Hi, this is Juan Tutors, and today we're doing the June 2024 Earth Science Regents, the regions that just happened just a few weeks ago. So I know some of you are going for the August 2024 regions, and some of you are going for future regions. Whichever is your situation, I want to wish you good luck, and I want to say that if you do follow this whole video, you will do a lot better on the regions than other students who don't follow any videos at all. I do want to address how to use this video as much as possible, but I'm gonna do that as I'm doing problems. We're gonna just jump right into the problems. But before we do that, I just want to make sure that you do obviously have to use your knowledge of Earth science because this is an Earth science regent. So that's not too surprising, right? But another thing, you are required to have and use the reference tables for the Earth science regents. Here is my reference table, and we're going to use a digital one for the purposes of this video. Obviously, you have to go into that one. I don't know why it's a thing that some students just don't bother using the reference tables. It's an absolutely required part of it. And in terms of use of time, it is worthwhile to spend a little extra time on the going into the reference table than it is to, let's say, for example, not use the reference table and maybe just get lucky, or not get lucky, maybe just get it completely wrong by not using it. But the other one, if your school decides to play some funny business in terms of having access to a four function calculator, you are required to have access to a four function calculator for this test. Okay, so do understand that your school is required to do that, to provide that, and of course the last thing, to use the word or expression that of those given best completes the statement or answers the question. Okay, so from that we're going to just jump into numero uno, number one. The diagrams below represent the atmosphere and inferred interior structure of the planet Uranus. I know most people pronounce it Uranus, but it's actually Uranus. And I look at the diagram real quick and then I go back if I need to. The outer atmosphere, the upper cloud layer, the atmosphere, hydrogen, helium, and methane gas, then the mantle, water, ammonia, and methane gases, and the core, which is silicate, iron, and nickel rock. Now, and I see this, that's Uranus. Okay, perfect. Which two factors caused the inferred layered structure of this planet in our solar system? One, gravity and eccentricity of the orbit, or two, gravity and density differences of materials, or period of rotation at the equator and eccentricity of the orbit, or period of rotation at the equator and density differences of materials. So the first thing I'm going to say, like I said, I would talk about how to use this video. One of the first things that I'm going to recommend is that I actually recommend pausing every single problem and choosing one of the answers, or equivalently eliminating all the answers that you think are wrong till you finally arrive at an answer. Choose one, stick to it. Don't say, I think it's this one, and then play. Say, I think it's this one, and this is the one I'm going to stick to, or I know it's this one, and therefore this is the one I'm going to stick to. Don't say, I think it's this one, and play. Why? Because I've actually worked with students who say, I think it's this one, and then I tell them that it's actually another one, and they're like, oh, I knew it was that one. Well, then they're lying to themselves because they chose one answer, but then convinced themselves that it was this answer, and they knew that it was this answer, but then also, if I had told them that this one was right, they would have convinced themselves that that one was the answer. So you have to choose one and commit to it before you could say that you were right or wrong. And you don't have to say, I know that this is the answer, but you have to commit to it by saying, this is the one I'm going to choose. So I recommend doing that for every single problem. Now, I'm going to go on to this question. This is how I go about um, answering this kind of question. I want to point out that this is actually what's called a two by two question. Notice that the first two phrases are, for choice one and two, is gravity and gravity. For choice three and four, it's period of rotation, period of rotation. And for choice one and three, it's eccentricity of the orbit. And for choice two and four, that's density differences of material. So you don't have to go through this diagram. In fact, I highly recommend not going through this diagram that I'm about to draw while you're taking the test. But in order to explain it, I have to go through the diagram. Okay. Wow, that's a terrible straight line. Okay. So, but top, I'm going to say gravity and period of rotation. And on the left, I'm going to say eccentricity of orbit. And on the right, on the fourth one, I'm going to say differences, density differences. So now notice in this case, choice one is gravity and eccentricity of the orbit. Choice 2 is gravity and density differences. This is choice 2. Choice 3 is period of rotation and eccentricity of the orbit. And then choice 4 is period of rotation and density differences of the orbit. So the reason I call this a 2 by 2 problem is that if the choices are formatted so that you're not answering one thing, you're actually answering two things. Which two factors cause the inferred layer structure of the planet and the solar system? So you could actually do this question not by knowing the two factors, but by knowing each individual factor individually. So you could actually analyze each factor individually. So how do I analyze this problem? I know that the orbit of, let's say, moons or satellites, either natural satellites like moons or man-made satellites that we actually send to Uranus to take pictures. So those orbit at a certain rate, and actually those actually end up measuring the gravity of Uranus. So I know that gravity is a very possible answer. But the period of rotation, a lot of students, I was even debating it while I was practicing for this test and practicing for this video. And I was debating, I'm like, the period of rotation, shouldn't that tell us a little bit about the inferred layer structure? And actually, though, the period of rotation tells us a lot more about the way the planet was formed. So the meaning by accretion. So because it was formed by accretion, it has a faster rotation rate. So period of rotation doesn't actually tell us, though, much about the layers. After all, the gravity could be, well, okay, so let's move on from that, because I could actually go on and on and on about it. How about this eccentricity of the orbit? The eccentricity of the orbit being circular or being highly elliptical, in the case of planets, the orbits are highly, or very circular. They tend to be very, very circular. But that tells us nothing about the layers. That's just the way the planet goes around the sun. I mean, there's plenty of asteroids that go around the sun in a circular orbit, although many of them do have a bit of an eccentric orbit. But the eccentricity of the orbit doesn't tell us anything about the layers. But the differences of materials, the density differences of materials, that does. Because what happens is that anyway, so we crossed out this. Let's just talk about the 2 by 2. Crossed out that, and we also crossed out the eccentricity of the orbit. So that leaves us one choice. So notice we answered two questions. But before we select number 2 officially, what is it that the density differences of materials tell us? Well, as we know that when we pour, let's say, like water and oil in a cup, it doesn't matter whether we poured the water first or the oil first. The oil is always going to end up on top, and the water is going to always end up on bottom, assuming you're using like cooking oil and not some other esoteric oil. Why? Because the density of oil is lower than the density of water, so that the oil immediately goes to the top, and the more dense water immediately goes to the bottom. So that's what happens with planets as well. The denser stuff goes down towards the core, and the less dense stuff stays up. So now I want to point out which one of these has only check marks. Only number 2 has check marks, where all 1, 3, and 4 have are crossed out. So on that note, I want to point out the strategy that we just used to answer that question. The strategy that we just used to answer that question was we crossed out any answers that we knew to be wrong. That question we ended up answering not just by knowing that these two things have an effect on creating the layers of Uranus, but that the other ones had something that didn't make sense for the problem. That is actually something that's much more relevant in terms of a test taking strategy for the science classes than they are for the math classes. Although for the math classes, which I do tutor, JuanTutors.com, which I do tutor and I do teach, it's a useful strategy, but it's way more useful in the sciences. Number 2, which process occurring in the sun produces energy by converting lighter hydrogen into heavier helium? Is it radiation? Is it conduction? Is it radioactive decay? Or is it nuclear fusion? So how we need to know what some of these words mean. So let's actually just talk about what some of these words mean. Radiation is the emission of energy, not the production of energy, but the emission of the energy. Yes, when hydrogen is when hydrogen merges with another hydrogen to produce helium, yes, energy comes out, and yes, some of that energy is in the form of photons. Not all of that energy is in the form of photons. Some of it is neutrons. Um, and the point is that that is not the process that is being undergone here. That's only a small part of it. That's only like literally this part of it. So what is conduction? Conduction is not a production of energy. This is a movement of hot and cold stuff. No, that's a lie. That's a lie. That's no, that is true. That's a movement of hot and cold stuff. Yeah, sorry. Uh, no, that's convection. Wow, I just messed that up. So about this video, I'm not doing any edits to the video. If I make a mistake, I will make sure to catch every mistake that I make because I do have a ton of notes here. Okay, so let's see. This is what my notes look like. Tons of writing. You don't have to be able to read that, so it stays blurry. That's okay. But I'm not going to edit any faux pas that I make because the more that I don't edit, the more that I could record. And in most seasons, most region seasons, I want to record 7 videos. I literally usually get to 1 or sometimes 0. Sometimes I almost finish a video and then the season's over and I don't upload anything. So conduction, I'm sorry, is the flow of energy through physical contact. So a hot thing touches a cold thing, and the hot thing transfers some of its energy to the cold thing. So energy flows from hot to cold. So that's not a producer of energy. So that's not it. Okay. Now, radioactive decay versus nuclear fusion. So, one of these, radioactive decay can produce energy, and nuclear fusion can also produce energy. Radioactive decay pretty much always does produce energy, but decay is a breakdown of heavier elements into lighter elements. So that's not what's going on here. Here, hydrogen is fusing into helium. Helium is the heavier one. But nuclear fusion, this is the merging. And now the word, by the way, the word fusion does, in non-science terms, does mean the combining of two different objects. So this, you're merging two hydrogen atoms to make helium. So this is the merging of smaller elements into heavier elements. Okay, so this is definitely a nuclear fusion situation, and the radioactive decay doesn't is not the answer. And we have a picture of this just so that we see it. Deuterium, which is a hydrogen with 1 neutron, and a tritium, which is a hydrogen with 2 neutrons, merge together to form this activated complex of a helium with 3 neutrons and 2 protons. And then pretty much immediately, one of the neutrons gets emitted, and then a stable helium atom, a stable helium nucleus emerges, and a ton of energy is released. A ton of energy is released. Um, Fun fact, I learned this a long while ago. The amount of energy produced per unit volume inside the sun, you would think that it's just this enormous number. I just said that an enormous amount of energy is released by this. And I do mean enormous in terms of the amount of matter that's used compared to, for example, chemical reactions. Physical reactions tend to produce a whole lot more energy compared to a chemical reaction. Uh, Mega electron volts versus electron volts. Okay, but the amount of energy per unit volume inside the sun uh, is about the same amount of energy being produced in an active compost pile. In an active compost pile, literally, you have worms and all that stuff, and bacteria's working on decaying plant matter, and about the amount of energy being produced in that um, pile is the same amount of energy produced per unit volume in the sun. So why is the sun thousands of degrees hot, whereas the compost pile is not? Now, do understand the compost pile, even as small as it is, can get really hot. In fact, it can get so hot that it spontaneously combusts, and that is a problem for a lot of farmers. A compost pile can spontaneously combust, which means it can get hot. So clearly the sun can also get hot. And why does the sun get hot? It's sheer volume. The volume of the sun is so big that it keeps so much of that energy, and then it got hot. So that's literally how active the sun is. Number three, compared to the size and periods of revolution of the terrestrial planets, the Jovian planets have smaller sizes and shorter periods of revolutions, or smaller sizes and longer periods of revolution, or larger sizes and shorter periods of revolution, or larger sizes and longer periods of revolution. This is yet another 2x2 problem. The question is, do the Jovian planets do they have smaller sizes or larger sizes? Okay. And also, do they have shorter periods of revolution or do they have longer periods of revolution? Okay, so being a 2x2 problem, I'm going to go ahead and answer this one very strategically. The Jovian planets, you do need to know what the Jovian planets are. Okay, so there's some vocab. Jovian planets. Well, that's equal to Jupiter, Saturn, Uranus, and Neptune. Okay, so what do I know about Jupiter? It's huge. That's one thing. And the Great Red Spot, but it's huge. It's huge. So compared to the sizes and periods of the revolution of the terrestrial planets, the Jovian planets. So we are answering about the Jovian planets. Now, I'll tell you another place where students get stuck on this question. This is a really important one because I did not get stuck on this question when I was doing it. However, there are a couple of questions that when I was reviewing them, I did catch myself accidentally getting them wrong in my practice because they say compared to this other thing is what? Make sure you're answering the question about the thing that they're asking. They are asking about the Jovian planets, not the terrestrial planets. They're asking about the Jovian planets relative to the terrestrial planets. So the Jovian planets are definitely huge. Okay, so they don't have smaller sizes. They don't have smaller sizes, so that crosses out 1 and 2. And then the second thing, do they have shorter periods of revolution? Now, you do need to know what the period of revolution is. This is like the sun. And then the period of revolution is the orbit time. I ran out of space here. Revolution. Period of revolution. So if this is, let's say, Jupiter. Okay, how long it takes for Jupiter to go around the sun. So, well, I do know that the further out that you go from the sun, the longer it takes for the planet to go around the sun. Our period of revolution around the sun is literally a year. That's actually our definition of a year, how long it takes for the Earth to go around the sun. And Jupiter's year is about 12 times longer than our year. So the Jovian planets have a longer period of revolution. Longer. So cross out shorter, that crosses out 3. Larger and larger and longer period of revolution. The only one that has 2 check boxes is number choice 4. And on that note, here's the subscribe button. Oh, perfect. 833 subs. So this might go up and might go down while I'm recording. I just bought this thing. I'm really excited about it. It tells me how many views I've had and how many subscribers and also the time, which is convenient. I just bought it, which I'm really excited about. As you know, YouTubers, one of the first goals for YouTubers is to get to 1,000 subscribers so they can monetize things. And I always tell my students when I'm recording these videos, I always tell them that the reason that I am doing these videos is because I always wanted a free part of my tutoring business. I have a paid part of my tutoring business. If you go to JuanTutors.com, you can hire tutors. But I've always wanted to give something away for free. That's been part of my philosophy for my whole life. So if you do appreciate this video, especially if you make it to the end of the video, I'm going to ask that you do subscribe. If you feel like I deserve it, that's when you should subscribe. Only if you feel like I deserve it. So, but on that note, we're going to go to number 4, número 4. The photograph below shows a dust-covered icy object that has a highly elliptical orbit in our solar system. That's a cool little rock there. Big rock. The celestial object is most likely a comet that leaves a trail of particles in space, or a meteor that leaves a trail of light across the sky, or a moon that revolves around the planet, or a planet that revolves around the sun. So I'm going to use some context clues here. So they say that it's a dust-covered icy object that has a highly elliptical orbit. Okay, so that being that, comet, I know comets tend to have very highly elliptical orbits. They tend to come closer to the sun and leave a nice what looks like a trail in the sky for a few weeks, but they move really slowly, and then they leave, and then they come back after sometimes maybe 20 years, sometimes 50 years, sometimes 77 years, I believe, something like that for Halley's Comet, and sometimes some of them literally 10,000 years. So Comet is looking good. A meteor that leaves a trail of light across the sky. The moment that the meteor leaves a trail of light across the sky, its chances are that it's going to be completely destroyed by the atmosphere of the Earth. So more than 99% of the time, far more than 99% of the time, far more than 99.99% of the time, they get destroyed by the atmosphere. And the ones that you see leaving a trail in the sky, believe it or not, they tend to be the size of dust to pebbles. Pebbles. And sometimes we get unlucky and we get like a Chelyabinsk meteor. Those could be a lot bigger, 10 meters to 50 meters wide. If it's 50 meters wide, we're not going to have a good time. 50 meters wide, yeah, we're not going to have a good time in that situation, or at least locally. And then, of course, they can get a lot bigger. We know the meteor that struck, or the comet that struck in the Yucatan that killed off the non-avian dinosaurs 66 million years ago. So that one doesn't make sense though. Now, a moon that revolves around a planet. This one says highly elliptical orbit uh, in our solar system. This one, the thing is that a moon revolves around a planet, not around the sun. Okay, so it can't be a moon. So far we've eliminated two. And finally, a planet that revolves around the sun. The planets, we already know what the planets are: Mercury, Venus, Earth, Saturn, Uranus. No, Mercury, Venus, Earth, Saturn, Jupiter. Um, I got it wrong. Hold on. Mercury, Venus, Earth, Mars. That's why I kept skipping that one. Then Jupiter, Saturn, Uranus, and Neptune. Those are the 8 planets. And I know that we, in our heart, some of us want to include Pluto, but we no longer do. So we got the 8 planets, and maybe we'll discover a ninth by the time you watch this video. Um, but those 4 planets, we know what they look like. We've seen them mostly in pictures. None of them look like this. They all look like nice circular with different looks. So it can't be a planet around our sun. Nope. So the only one that makes sense is a comet that leaves a trail of particles in space. This comet is the Comet 67P Churyumov-Gerasimenko. It was taken. That picture was taken by the Rosetta spacecraft. So I remember being really excited to see this picture, and I did not expect it to look like this. But yeah, this is what it looks like. It's one of the least active comets that we were able to observe. The reason we went to observe a less active comet is that we have gone to more active comets. We've gone to Halley, comet Halley. Um, is But the thing is that the more active they are, the more dust that they have going around them, which means the less that we can see the comet themselves. Whereas this comet had just enough of a lack of activity that we could see its surface with a lot of clarity. Okay, so number 5. At which location will the sun appear to pass directly overhead for an observer? Northern Asia, Northern Australia, Southern Greenland, or Southern Antarctica? Look, if you can answer this question just by personal content knowledge, great, good for you, proud of you. The only thing that I could do at this point, I have a 1 in 4 chance of getting this right if I just guess. But if it appears to pass directly overhead, that means that we have to be close to the equator, right? So I know that, remember, directly overhead for an observer, that means that southern Antarctica can't be it. Southern Antarctica is a very cold place, and it's very far from the equator. It never crosses, it doesn't even come close to uh, the equator at all. So now I went from a problem that I have a 1 in 4 chance of getting it right to a 1 in 3 chance of getting it right. I remember every time I see a map of the Earth, I always see that giant looking Greenland, which Greenland is not as huge as they make it look in maps, but I know that Greenland is further north than New York. So southern Greenland, the sun is never perfectly overhead for New York, and that's an important thing to know. The sun is never perfectly overhead. It can come close. It can come within about 20 degrees of being directly overhead, so it can almost feel like it's directly overhead. But the reason you know it doesn't never comes directly overhead, you've never been in a situation where you stood on the ground and looked at your feet and didn't see a shadow. And that might be a weird thing to say because you might say that can never happen, except actually that in a huge chunk of the earth that happens twice a year. Um, you have to be below the Tropic of Cancer or above the Tropic of Capricorn. I don't know if I got the order of those right now that I'm thinking about it. You have to be between the Tropic of Cancer and the Tropic of Capricorn. So the answer is either Northern Asia or Northern Australia. And knowing what I know about my map, I don't think it's Northern Australia or Northern Asia. So I'm starting to suspect that it's Northern Australia. So let me talk about the notation that I use. This is test taking strategy. I know that different people have different notations for crossing things out or marking things that I think is wrong or I know is wrong. I want to point out that I crossed out number 3 and number 4 on the number because I know for a fact that those are not right because southern Antarctica is way too far from the equator, and southern Greenland is way too far, is north of New York. So that can't be it either. Now, the reason I crossed out Northern Asia next to Northern Asia is because I'm simulating myself as a student. Okay, I do know where Asia is, so I happen to know that this is not the right answer. But so fake student me, when I talk about fake student me, I'm simulating myself as a student. So fake student me says, I think that Asia is actually pretty far north because it's north of Africa. I don't know how north or south Australia is, other than that Australia is basically in the southern hemisphere. But I think that Asia is pretty far north, being north of Africa for the most part. Um, I think that one's going to be wrong. So I put the X next to that answer because I think it's wrong, and I could put a checkbox next to this answer because I think it's right. Okay. So as opposed to if I know it's right, I would circle it, but I didn't circle it because I don't know it. How do I confirm it? This is the first reference table problem. So if we go uh, to the reference table here, okay. Now we go to page, this is a slow scroll here, okay. Page 4. Page 4 should be good. I'm going to rotate this, okay. And if you look for the different parts of the world, so here's southern Antarctica, very, very far south, almost 100% below the Antarctic Circle. There's these little nubs that go below the Antarctic Circle. Uh, and then the vast majority of the Antarctica is below the Antarctic Circle, south of the Antarctic Circle. So that is not the answer, as we confirmed. Here's Greenland. Here's New York. There's actually a gray. They actually did really a good enough resolution here, I guess because they know that they have to have a good map of New York, being that this is a New York State test, that they have to have the slightest bit of Long Island showing. So even though some islands are just too small to show, they actually made sure to show New York, which is nice. Either way, Greenland is up here, almost all of it above the Arctic Circle. And so that's definitely not the answer. So the answer is either Northern Asia or Southern Asia or Southern Asia, no, Northern Asia or Northern Australia. And that context clue, Northern Asia, should have actually been the hint that confirmed that that one was wrong. Because if you go, I said north of Asia is mostly north. I don't know how far north. And actually, now that I'm looking at it, I do see that some of Asia, uh, you do see the sun overhead, but this is the southern part of Asia. India is part of Asia, and parts of India do see the sun right overhead, but northern Asia, oof, goes all the way into the Arctic Circle as well. So Northern Asia does not see the sun overhead. And nowhere above this dotted line will ever see the sun overhead. And nowhere below this dotted line will ever see the sun overhead. So, but however, Northern Australia, remember, Australia is already in the South Pole. I'm sorry, in the Southern Hemisphere. So Southern Australia is closer to the equator than Southern Australia. And if you see half of Australia, approximately, it's more like maybe 30% of it is above the 23.5 degree line. So they do see the sun overhead. So the answer is, in fact, Northern Australia. Okay. And again, the context clue of Northern Asia would be enough to hint to us that choice one is not the answer, even without the reference table, but I highly recommend using the reference table. Numero 6, number 6, the hydrosphere covers approximately 70% of Earth's atmosphere, or 70% of Earth's lithosphere, or 85% of Earth's atmosphere, or 85% of Earth's lithosphere. I've seen students trick themselves into getting the wrong answer here. You know, does the ocean cover the atmosphere or the lithosphere? Does the ocean cover the air? I don't see the ocean above me, right? I'm breathing in the atmosphere, and the ocean is not above me. So the ocean does not. The hydrosphere is the ocean, right? Oh, this is the ocean plus the rivers plus all water. So the hydrosphere includes rivers, lakes, ocean, and it includes underground water. But in terms of the covering, it doesn't cover a single bit of the atmosphere. Okay, so being a 2 by 2 question, I've already eliminated a question, eliminated two choices, and now the question now is does it cover 70% of Earth's atmosphere, or Earth's lithosphere, the rock layer, or 85% of Earth's lithosphere, which again, litho is equal to the rock layer. Okay. Now, before I tell you what the answer to this question is, I want to talk about what I call a passing problem. A passing problem is a problem that leads you towards a passing grade. So how can we how could we possibly determine what a passing grade is? Well, actually, there's a table of values here. Now these numbers are very small. Here is what a perfect grade looks like. You took the performance assessment and you got a perfect grade on that, and then you took this Regents, which is the written assessment, and you got a perfect grade on that. Then that's how you get 100. Okay. So, and of course, there's the opposite of that. If we scroll all the way down, we got a 0 on the performance assessment, and we got a 0 on the Regents, and that's how we get a 0 on the Regents. Now, how do we determine? Well, we've got to have a way to determine kind of what a passing grade is, given that we're not going over the performance assessment, we're only going over the Regents. Well, notice that the Regents depends, the final grade depends on the performance assessment. Well, what I'm going to do is I'm going to assume that your approximate grade on the performance assessment is proportional to the approximate grade on the Regents. If yours is not that, or like, for example, if you already know your Regents grade, then you could actually just look at the correct column. But the way I'm going to do it, if they're proportional, I go right down the diagonal, which goes to the middle, which is already a 68, and then keeps going down the diagonal here. So what's halfway? Actually, halfway down and halfway to the right gives us an 8 and about a 44. And halfway down also gives us a 8 on the performance assessment and a 43. And a 43 happens to be almost exactly half of your total Regent score, 85. In fact, the one right below it is slightly less than half, and the 43 is slightly more than half. So actually, this is exactly basically where the middle is. And so the number of points that you need to pass this test is 43 out of 85, or in other words, exactly half of the multiple choice. And exactly half, yes, plus or minus a half a point. Fine, exactly half. So, which means that if you get to a point where you have a 50-50 chance of getting the question right, because you've eliminated two incorrect answers, that problem is no longer a problem that either statistically lowers your grade nor increases your grade statistically. And it leads you towards that average, that exact average that gives you a passing grade of 65. So a passing problem is a problem that you have a 50-50 chance of getting it right. And this problem 6, numero 6, we have a 50-50 chance of getting it right, so it's a passing problem. So we want to do that with as many problems as possible. Sometimes you could eliminate one choice, which gets it closer to passing problem, and definitely a worthwhile strategy. After all, if you get 25% of the points on average, that's about 21. So 21 on average will get us around like a 40 on the regents. But if you have 1/3, if you eliminate one choice, then on average, that's 1/3 of the 85, which is about 28-ish points, which gives us a 50. That's a lot of extra points. But of course, if you go to a 1 in 2 chance of getting it right, on average, that gives us that 65 that we just talked about. So that's why getting to a 50-50 chance of getting it right is a passing problem and definitely worthwhile. Now, I put a picture of the Earth here because we can actually see that most of the Earth is covered by water. But this is something I looked on the reference table to see if I saw that number, but I don't see it. So this is something that you just want to know. This is your knowledge of Earth science. About 70% of the Earth's lithosphere is covered by water, and about 30% of it is land. Okay, so that's just something you kind of have to know. Excuse me. I'm not deleting any of those coughs, anything like that. This one is an interesting question because had you taken this Regents, let's say 200 years ago, before the Regents existed, you might have had different opinions about what this picture was. So let's actually talk about this picture. Numero 7, number 7. The photograph below shows a 1-mile diameter feature on Earth's surface. What is this feature and how was it formed? Was it a dry kettle lake formed from an impact event, or a dry kettle lake formed by a retreating glacier, or a crater formed from an impact event, or a crater formed from a retreating glacier? This is yet another 2x2 problem. Dry kettle lake or crater, and impact event or retreating glacier. Okay, so again, this is one that you this is your knowledge of Earth science, but this is a very classic image that we should be comfortable with recognizing. This is called the Barringer crater. The government tried to make it a public land, I believe, but it is owned privately. This crater, believe it or not, is owned privately. I think had they not been taking extremely good care of it, maybe the government would have taken it from the family. But in fact, they're doing a very good job at taking very good care of it. So I really appreciate them for that. This is a crater, absolutely a crater, and we want to be able to recognize it as that in Arizona. Okay. Yes, this is in the United States, and the people who were around about 50,000 years ago, well, there were no people around in Arizona 50,000 years ago because we were still in Africa and perhaps Asia and Europe. There were definitely Neanderthals up there and others, but I believe humans, I want to say humans were still in Africa 50,000 years ago, but I don't know if that's true. But that said, it is a crater. Okay, it is a crater. So a dry kettle lake is not that. Okay, but now the question is it an impact event or a retreating glacier? There are dips in the land formed by retreating glaciers, but retreating glaciers don't tend to make very nice circular holes in the ground. They tend to gouge out uh, in land in lines, and then deposit land in lines as well. So this is actually a really very massive impact event. And if there were people in this area, which again there weren't, but the animals that were in this area when this impact happened did not have a good time. And it is very possible that people in Africa and perhaps the Neanderthals also in Europe and Asia also did not have a good time after that impact, because it definitely would have had an effect on the weather in the Earth. Okay, so but luckily not for too long, and obviously humans survived it. So numero 8, number 8, a time-lapse photograph shows stars as they appear to move around the central star Polaris. Okay, so And for the rest of this test, and I'm going to use the context clues because the test is actually quite long. So I'm going to say around the central star Polaris. So they told us it's around Polaris. And right there is the central star Polaris, right around there. And you see that Polaris is actually kind of a bright dot. Polaris is kind of like a medium brightness star. It's not even like the super brightest star in the sky, nor is it the least bright star in the sky. It just happens to be right at the kind of within a few tenths of a degree from the center of rotation of the Earth. Polaris does not appear to move in the nighttime sky because Polaris is located in our solar system, in our galaxy, or above Earth's axis of rotation, or above Earth's equator. Now, in terms of context clues, here's the thing. In our solar system, we want to be able to eliminate this one right away. We have to know that this solar system is our star, plus all the planets orbiting our star, plus all the moons orbiting our planets, plus all the asteroids and comets orbiting our star, which is the sun. We only have one star in our solar system. Okay? Only star in our solar system is equal to the sun. Just the sun. That big bright ball in the sky is the only one. Now, it doesn't appear to move because Polaris is located in our galaxy. It is located in our galaxy, but that's not the reason why it doesn't appear to be moving. After all of those stars are also in our galaxy. The stars that we could see as single points in the sky are also in our galaxy. If you look at any other galaxy in the sky, it might look like a little bit of a smudge, and with maybe a bit of a central dot. So maybe you might look and think, oh, it actually does look like a star. But the stars themselves that we could see as individual dots with our naked eye are all in our galaxy, all of them. So all of these dots, except for maybe let's say a few, are in our galaxy. The few that are not in our galaxy are literally galaxies themselves, very far away. So that's not it. The next one, above Earth's axis of rotation or above Earth's equator. Above Earth's equator, the stars move. The stars move fastest over the sky. Above Earth's axis of rotation, well, those are the ones that seem to not be moving. Those are the ones that seem to not be moving, or move less. So the Polaris is right above Earth's axis of rotation, right above the North Pole. If you are in United States, there's you could follow arm of the Big Dipper to actually point towards or you could follow, yeah, an arm of the. Now I'm afraid to misquote myself. Either the Big Dipper or the Little Dipper. I think it's the arm of the Big Dipper or the pot of the Big Dipper to point towards the North Star. And it's about 45 degrees up because we are about 45-ish degrees up, depending on how far up north or south you are. So, but if you are literally in the North Pole hanging out with Santa, if you look straight up, perfectly straight up, you would see Polaris every single day, and it wouldn't move from that spot. Whereas for us, we would see Polaris in the same 45-ish degree spot in the sky, also not moving. All right, numero nueve, number 9. The map below shows 5 locations labeled A, B, C, D, and X on Earth's surface. Solar noon is occurring at location X. Okay? And at which location is the time 2 p.m.? 2 p.m. Okay, so this is the one that I think requires maybe a little bit of algebra, but the question is point A, B, C, or D. Okay? So you have to know that there's 360 degrees in a circle. And therefore 360-degree lines of longitude around the Earth. Okay? There's also 24 hours in a day. So you might wonder, how many degrees does the Earth pass every single hour? 360 over 24 hours is equal to 15 degrees per hour. So every hour, the sun passes over the Earth 15 degrees. And that therefore eliminates anything, we need to know 2 p.m., that's 2 hours later. That's 2 hours past solar noon, okay? And this is at the same time that that this picture is taken. But it means that this is, well, 15 times 2 is equal to 30 degrees away from X, okay? Which means that the answer could be A in principle, or it could be D, but it eliminates C and eliminates B. So we could eliminate those immediately, B and C, which is nice because now we have a passing problem. But now the question is, which one is it? Is it A or uh, is it A or D? Well, this time we also have to know which direction the sun travels. So the sun rises in the east and it sets in the west. So in the sky, the sun is traveling in that direction. So if the sun is traveling in that direction, well, that means if the sun is overhead, if the sun is over, let's use yellow, over X at noon, then 2 hours later, it's going to be over A. If 2 hours later is going to be solar noon at A, then right now, the time, right now at point A, it's 10 a.m. So this is 10 a.m. But also, the sun used to be uh, above the 60-degree mark over here 2 hours prior. And in fact, this entire line of latitude, line of longitude. So that means that at point D, it was 12 o'clock 2 hours ago, which means that it's 2 p.m. right now. They said is the time 2 p.m. Okay, so the answer is choice D, choice 4, 2 p.m. Okay, so that's one of the problems that you might need a little calculator for. That's why if your school insists on not providing calculators, they really do have to provide you those calculators. Okay. All right, número 10, number 10. Approximately how many degrees per day does the Earth move in its orbit around the sun? 1 degree per day, or 50 degrees per day, or 24 degrees per day, or 360 degrees per day. So now this is the Earth moves around the sun. The Earth is going around the sun. So if this is the sun, and this is the Earth, it goes around the sun in how many days? 1 year, which is equal to, you do have to know this, 365 days. Now, you do have to know that the 1 year is 365 days, although I have taught students who didn't know that 1 year is 365 days, which, yes, despite the fact that it's perhaps unfortunate, we can go to the reference table. Let's see. And they have a table with the information about our planets. Let's rotate this back. Okay. Information about our planets. Where does it go? There we go. And we see that the Earth's period of revolution around the sun is actually 365.26 days. Okay, let's actually add those decimals for the purposes of this problem, 0.26 days, which is around 365 days. Okay, but the 0.26 is the reason we have those leap years and that weird formula for the leap years. So, well, if it goes 365 degree 0.26 days in 1 year, and also a full time around the circle is 360 degrees. So how many degrees per day? That's 360 degrees per 1 day. Okay, and that's, or I'm sorry, per 365.26 days. Now, I can see already that that number should be somewhat close to the number 1 because the denominators are really, the numerator and denominator are really close to each other. But 360 divided by 365.26, And that's very, very close to 1 day. Okay, 0.99, 0.98, then a 5, which rounds to 2 degrees, and this is around 1 degree. So then the answer's got to be 1 degree. Okay, per day, just 1 degree per day, or the Earth going around the sun. All right. Número 11, sorry, number 11. Which motion explains why some constellations appear in the sky only during specific seasons? Is it that the Earth revolves around the sun? So again, the keywords, hold on. Appear in the sky only during specific seasons. Only during specific seasons. So we know that Pisces, despite the fact being that it's the March astrological sign, it's literally not visible for most of the night during March, which is weird. I don't know why that is. Maybe somebody can comment on it and let the rest of us know. But for now, the sun revolves around the Earth. Actually, that does make sense, because if the sun revolves around the Earth, then at different times of the day, a different part of the sky is going to be visible at night, right? Uh, because for other parts of the night, the sun's going to be in the way. Like, for example, if Pisces happens to be blocked by the sun, we can't see Pisces. So the second one, Earth revolves. Wow. Except when I read it in my mind. The Earth revolves around the sun, even though I have it in my thing. The Earth revolves around the sun. The sun does not revolve around the Earth. The sun basically stays still while the Earth goes around the sun. So the Earth revolves around the sun. That's what that meant. The Earth revolves around the sun. The next one, constellations revolve around the Earth. That is a common misconceptions, especially among people who believe the Earth is flat. The Earth is definitely not flat. The constellations do not revolve around the Earth. Um, the constellations basically stay still. So the constellations do not revolve around anything, and the constellations again do not revolve around anything. So that one doesn't make sense. So definitely the only one that makes sense is that the Earth revolves around the sun, and again that is the reason. The Earth going around the sun means that the sun is going to block some constellations at different times of the year, and also be on the opposite sides of the constellation at different times of the year. So then those constellations will be most visible. But number 12, what is the relative humidity when the air temperature is 20 degrees and the wet bulb temperature is 11 degrees? Now, this is a pretty low humidity, um, but these answers are also pretty low, 9%, 2%, 17%, and 30%. So I'm not terribly comfortable with eliminating any of these answers, although I strongly personally suspect 2% and 9%. I feel like they're probably too low. This is fake student me saying that, but I'm still not fully confident with deleting any of those answers. And 2% is a pretty rare low humidity to have. But we go to page 12. There's no way to know that, I think, in a real life situation, right? So we go to page 12, the relative humidity and dry bulb and wet bulb temperature. So now I noticed that this one is talking about the dew point and the relative humidity, okay, as a function of dry bulb temperature and the difference between the wet bulb and dry bulb temperature. So I know I'm going to have to take the difference between the dry bulb and wet bulb temperature. Here's the air temperature, and here's the wet bulb temperature. The air temperature is, this is, that? The air temperature is the dry bulb temperature. And this wet bulb temperature, why is it called the wet bulb temperature? This is literally the temperature being taken by a literal wet bulb. So what is the bulb? If you ever seen a thermometer, the end of a thermometer has like a little metal piece or sometimes a glass piece that's highly conductive of temperature. So that is the bulb. A dry bulb is when literally the bulb is not wetted, and then the wet bulb is literally when the bulb itself is wetted. So how do they wet it? They usually don't like dip it in water. But they literally put a wet paper towel. For us in high school, they usually put a wet paper towel around it or a wet sponge around it, and they either spin it around the air or they blow a fan at it. so that some of the air, some of the water on the bulb evaporates. And as the water on the bulb is evaporating, well, the only molecules of water that come off the wet bulb are the ones that have more kinetic energy, which means the ones that remain are the ones that have less kinetic energy. And if you've done any physics or now you're listening to me, you know that that means that they're lower in temperature. So literally, when your hands are wet and you blow on your hands feel cooler. Or you're hot and sweaty and you blow a fan on yourself and your skin feels cooler because the water is literally evaporating and taking some of that heat with it. So the wet bulb temperature is a cooler temperature. And in this case, they said the difference between the two, 20 degrees minus 11 degrees, is equal to 9 degrees. That's equal to the difference between the wet bulb and the dry bulb. Okay, now I have to go to this table and they want the percent humidity, so the relative humidity. So I have to go into this table, okay? And I'm gonna paste this here. Okay, let's see if I can do that. Now I have to go now the dry bulb, remember the dry bulb is equal to the dry bulb temperature. Now, I do apologize for my handwriting being a little bit sloppy. I have worked on it, and this is the improvement. I know. But I'll do my best to write as neat as possible. But that said, the 20-degree dry bulb temperature is right here. So we have to go across, and then we have to go at the difference between the two, which is 9 degrees, and go down. And if we do that, let's do that with a highlighter so that we could actually see it. Okay, that's far enough. Let's go all the way. And then also, let's go down from here. And we see that we meet right here at 30. Okay, so the answer is 30. Is there a shorter way to do this problem? No, I mean, 20 minus 11 is 9, and then 20. Go to the table on page 12. I don't have to tell you the page number. You have to go. You just have to find it. Go into the reference table and find it. There's a hint to when you should go into the reference table. You're not expected to know that insane amount of detail. Maybe if you were taking an earth science class in, let's say, a geology class in, I don't know, college, or like an advanced geology program, then you might be required to kind of mentally know some of those things. Not in this class. You are expected to go to your reference tables. And in fact, even in real life, people just go to reference tables. You just have a lot more than just one reference table booklet. You have probably thousands of different tables out there. But numero 13, number 13, Earth's early atmosphere consisted of carbon dioxide, water vapor, hydrogen, and nitrogen. During this time in Earth's history, the first crust formed and was made of igneous rock. Based on this information, how did Earth's early atmosphere most likely form? Was it outgassing from volcanic eruptions or radioactive decay of igneous rock, or release of gases from plant life, or evaporation of ocean water? And I added this picture so that you would get an idea of what Earth possibly looked like at that time. And I see these rocks are darker. That's only for visual effect. They were probably so hot that they were glowing. So even at nighttime, you could probably see the rock. You've seen lava, so you know what the Earth looked like back then. Lava glows all on its own. They don't need the sun to glow to shine on them. So, is it outgassing from volcanic eruptions? Definitely, that definitely was happening at that time. Radioactive decay of igneous rock, but igneous rock doesn't decay. Because the things that decay are like the radioactive substances. As you know, uranium is one of them, plutonium is another one, and there are plenty of other radioactive substances out there. Carbon 14 is one of them. There's plenty, but the rocks themselves are not decaying. So that doesn't make sense. Now, the release of gases from plant life, I'm going to cross this one out immediately. There was no plant life. No plant life at that time. In fact, plant life didn't appear estimated until about 540 million years ago. Given that the Earth is about 4.5 billion years old, most of the Earth's existence did not have plants on it. So, and at this point, there's evidence that some life started very, very early, like very early, but not plants. So that doesn't make sense. Now, evaporation of ocean water, I could see why, in principle, a lot of students might think that. But the thing is, I don't even know how much of oceans we really had. There probably had to be some separation of the layers of the Earth before oceans were formed, and a lot of comet strikes would have also had to bring some water. However, they did say here carbon dioxide, water vapor, and hydrogen and nitrogen. Ocean water is made of H2O, literally water. So the ocean water really can only provide hydrogen and oxygen and other chemicals made of hydrogen and oxygen, not carbon dioxide because it doesn't have carbon, uh, and no nitrogen because the ocean really doesn't have much nitrogen in it. So this can't be it just based on the content. Okay. So the only one that remains, outgassing from volcanic eruptions, is the only one that actually makes sense based on the details that we know about the early Earth. And if it helps you to remember, this is what the early Earth looked like. So any questions that they ask you about the early Earth, just imagine this picture right here: thunder, meteors, asteroids coming in, comets hitting the Earth on an almost daily basis. Enormous amount of energy being um, absorbed by the Earth. Número 14, number 14. The subtropical jet streams are located in Earth's lower troposphere near 30 degrees north and 30 degrees south, or upper troposphere near 30 degrees north and 30 degrees south, or the lower troposphere near 60 degrees north and 60 degrees south, or the upper troposphere near 30 degrees north and 60 degrees south. So, if we look at, so it said subtropical jet stream, so that's a hint. Now, if we look at the map here, let's see. I put, there we go, page 14. So I'm going to be doing a lot of scrolling. I hope that scrolling doesn't bother you too much visually. I know that when other people are scrolling, that bothers me a little bit. So it does help to know um, that, well, first off, the troposphere is the layer of the atmosphere that we are in. Troposphere starts at the surface, and it goes about uh, about I'm going to say 25 kilometers up. Now, your teacher, depending, your teacher may have quoted like 20 kilometers up or 30 kilometers up, or they might have actually given you a range. And a range is a more accurate thing to say because the troposphere goes higher near the equator and it goes lower near the poles. So it does range from like about 8 to 30 something kilometers. So the average is around 25 to 30. So if they told you 30, fine. But point is, if we are at the surface, the troposphere does not blow on Earth's surface. I'm sorry, the jet stream does not blow on Earth's surface. So the lower, cross out any that's a lower troposphere. And so we're only left with upper troposphere. And now the question is, does it blow near the 30-degree mark or does it blow near the 60-degree mark? Now the subtropical jet streams, those are closer to the equator. So they are closer to the 30-degree mark. Okay. Is there another jet stream around the 60-degree mark? Actually, there is. Uh, those are the circumpolar jet streams. So there is another, so polar, they call it here the polar front jet streams. Now, could I have gotten this answer from this picture? Actually, absolutely. Because in this, on this reference table, page number 14, it actually says it right there. Subtropical jet streams pointing right here and right here. 30-degree mark, 30-degree mark. So we could have gotten the answer from this and not, I'm sorry, not that. So the only one that has two check boxes, upper troposphere and 30 degrees north and south, is choice 2. So numero 15, number 15, the transfer of heat energy in the oceans due to density differences is best described as conduction, convection, radiation, or insolation. Okay. So this one, I could see arguments why some students would think one thing versus another, but we do need to know a little bit of vocab here. So conduction is equal to a transfer of heat from physical contact. Now, a physicist might say, wait, conduction of anything from physical contact, like, for example, conduction of electrons, in a wire, sure. But we're talking about earth science. We are only worried about conduction of heat. So that one doesn't make sense. Convection is equal to the transfer of matter due to, and this is actually due to density differences. Now, you might argue that this is actually due to temperature differences, but actually, this is actually the transfer of matter due to density differences. So why is it that we talk about heat causing convection? Well, when you heat up something, it changes density. And if that thing is a liquid or a gas, then you have two layers that have different densities and they can convect. Okay? So there's a convection current that happens due to density differences. So I'm going to put in parentheses or other forces, because I'm like debating whether the Coriolis effect actually qualifies as convection. If you know whether the Coriolis effect qualifies as a convection current, definitely post it in the comments. Let the rest of us know. The Coriolis effect causes hurricanes and tornadoes in the northern hemisphere to turn clockwise. So is that a convection current? I don't know the answer to that. So please do post in the comments. But the transfer of heat energy in the oceans due to density differences best described as convection. That's starting to make a lot more sense. Now, this one, radiation, this is in the oceans. It is, I mean, theoretically possible that might be what happens, but we again have to use our knowledge of earth science. Transfer of energy within rocks happens through conduction, not convection, mostly. Although there is some convection, the moving of continents. But radiation, maybe in theory, but it's not actually how it generally happens. Radiation is the transfer of energy through the emission of electromagnetic waves. For example, heat, UV rays, infrared rays, light rays, radio waves, etc. That's not how the ocean actually transfers its energy. The hotter water and the colder water just kind of switch sides. And then insolation. Insolation. This was a new word for me. So we defined radiation. Insolation is the heating by the sun. This is not how energy is transferred by the ocean currents, by the ocean, due to density differences. Part of the heating happens due to the sun, but then how is that energy transferred? Well, that's through, again, we've eliminated every other choice, convection. Okay, Número 16, number 16. And by the way, if you're appreciating me giving you thorough definitions so that you can actually use them in the regions, please do hit that like button. Again, I do appreciate the subscribe button. Only subscribe if you feel like I deserve it. It does help me. I don't know if that counter has gone up or down. That counter actually is it's receiving the number of subscribers that I have automatically every second or so. This morning I had 831, so I've gotten 2 subscribers since. You hitting subscribe right now is not going to change that right now because I'm recording this and then uploading it. But if you are one of the 833 subscribers that I have so far, thank you very much. I really do appreciate it. It shows that you're actually doing whatever you need to do to get the best grade possible on this coming regions. But número 16, number 16, which list of Earth's materials indicates an increasing order of the amount of energy needed to raise the temperature of an equal masses of materials by 1 degree Celsius? Is it copper, iron, basalt, or basalt, iron, granite, or iron, copper, lead, or lead, basalt, granite? Now, if you know the answer to this question just from your mind, great job. I don't. Okay. But now I have to do increasing order in the amount of energy needed to raise the temperature of equal masses by 1 degree Celsius. Uh, I again, like I said, I don't know the answer to this question, but this is a reference table question, so that's okay that I don't know the answer to the question. If I go to page 1, and I go to, you have to know what specific heat means, okay? But I'm going to take this table for specific heat from the reference table. Now, if you didn't know that, again, all these like really particular numbers, the Regents doesn't really expect you to know these numbers by heart. That's not a thing. So it's okay if you didn't know that by heart. But what specific heat is, what is specific heat? This is the amount of energy required to raise 1 gram of a substance by that raise the temperature of 1 gram of substance by 1 degree Celsius. The temperature, TEMP, of 1 gram of a substance. So if the specific heat is lower, that means less energy required to raise it by 1 degree Celsius. So literally we have to go to the table and look up the specific heats of each of these substances. And let's go for the very first one. I mean, there's no sitting and guessing here. Honestly, it's physically impossible to guess at this. You go to copper, 0.38, 0.38, and a copper appears on this line, 0.38. Okay, cool. Then iron, 0.45, 0.45, 0.45, 0.45. Now already we can eliminate choice 3 because 0.545 is greater than 0.38. Let's make sure that we write this a little bit neater than that because we almost looks like a 9. 0.45 and 0.38. That eliminates that. And then basalt, we have 0.84, 0.84. Choice 1 is looking very good, 0.84. For the purposes of checking our answer, 0.84. Granite, 0.79. Oh, actually, we could eliminate choice 2. 0.84 is not less than 0.45. But now granite and lead. Granite is 0.79. And already we could eliminate this one. Okay. So the answer is actually choice 1 by reference table. It's the only way we could have done that one. Número 17, number 17. Which color and texture of surfaces with equal areas will have the least temperature increases when heated by the sun? Light color and smooth texture, light color and rough texture, dark color and smooth texture, dark color and rough texture. So again, least temperature increase. Least temperature increases when heated by the sun. I do hope that you know this, but if you think about what colors you wear when it's sunny versus what colors you wear when it's not sunny, in the winter you tend to wear darker colors, and that's not necessarily coincidence. The darker colors are actually warmer. Why? Because they absorb more energy from the sun. And why do we wear lighter colors? We tend to wear lighter colors during the summer because they reflect more energy from the sun, so they tend to stay cooler. So least temperature increases, color and text surface will have the least temperature increases. Okay, means lighter colors make more sense. Darker colors do not make sense. So choice 3 and choice 4 are eliminated, and now we have a passing problem. Now, smooth texture and rough texture. I get where there might be a little bit of debate. So sometimes we have to like kind of teach the controversy here, meaning, and there's no political controversy here, but what I mean here is what justifications we might have for choosing one versus the other, and I know why a lot of students would choose choice 1 versus choice 2 or choice 2 versus choice 1. Some students might recognize that if a surface has a rougher texture, when the sun sets, the rougher textured surface actually cools faster. That, though, is a justification why it would also heat faster when the sun is out. It heats faster because it has more surface to absorb light. And so the rougher texture literally can absorb more energy. And then when it emits the energy through radiation, it literally can radiate that energy right back to another grain of itself. So some of the energy, instead of being emitted straight up, some of the energy literally just goes to a neighboring grain. So a rougher texture actually is absorbs more energy. So a smoother texture stays cooler. So the answer is number one. Numero uno. All right. Número 18, number 18. Over the last 200 years, global warming is inferred to be primarily caused by strong El Nino conditions, or retreating glaciers, or an increase in greenhouse gases, or an increase in sea level. Now, I do apologize for the people who follow politics and believe that global warming is not real and not man-made. You are welcome to believe whatever political thing you want to believe. You can listen to whichever politician you want to listen to. And I know that when politicians speak things that jive with our political beliefs, or our moral philosophies, that we tend to believe their scientific opinions as well. But unfortunately, we are not doing this test based on even our politicians or our morals. We are actually doing this test based on what the data says. So, what does the data say? Data says global warming is real and man-made. Now, the one of the biggest contributors uh, global warming is carbon dioxide and also methane. Carbon dioxide is carbon dioxide, and CH4 is methane, a big component in the gas that you use um, to run your car. Um, why did I put pictures of cows for this one? Turns out that one of the biggest contributors of methane is all the cows um, that we uh, use to eat beef. They produce a lot of methane. They eat a lot of vegetable matter, and they literally ferment that vegetable matter in their guts, and they literally literally toots a bunch of methane, literally. So real and man-made, again, the data shows it. So if you choose to believe the politicians that say that global warming is not real and man-made, you're free to believe that. However, again, since we are doing the science, we're going by what the data says. We have to go by what the science says, and the science, the data, the evidence, all of it says that global warming is real and man-made. So global warming is inferred to be primarily caused by a strong El Nino occurrence, this would be natural. And strong El Nino conditions does have an effect, but El Nino conditions vary every 2 to 7 years. That wouldn't cause this increase in global warming. That would just cause a phasing up and down of the temperatures. Retreating glaciers is also natural. And the retreating glaciers don't cause the warming causes the retreating glaciers in that order, right? Your ice melting in the freezer doesn't cause your freezer to get warmer. You forgetting to close the door or the door just not quite closing right causes the ice to melt because the freezer got warm. An increase in greenhouse gases, this is the main cause. That's what all the data says. And then an increase in sea level. Again, this is natural. Now, in principle, this could have an effect on global warming, but again, it's natural. And in fact, right now, all the evidence seems to imply that the increase in sea level is for the most part due to the retreat in glaciers, which is partly natural, but now has accelerated due to global warming. So, in other words, the increase in sea level is not causing the global warming. In fact, there's debate about whether the increase in sea levels, for a lot of reasons, might cause more global warming or might cause less global warming, might even cause an ice age. We don't know. But either way, natural, man-made. The answer is number 18. Yeah, real, man-made. So they do expect us to know that. Whether your politics makes you believe that that's not true, you are welcome to do that. But that's not, we're doing science. We're doing data. We're doing database evidence. So, numero 19, number 19. The graph below shows predicted air temperatures and dew points for New York State during a 2-day period. And I do take a quick look at the chart before coming back to the chart. I see the title, predicted air temperatures and dew points. I see the temperature. And on the bottom, I see some times and I see some more times. Okay, good. And I see two lines or two curves, air temperature and dew point. Fine. Then that's all I take in before going back to the chart. Then I go back to the words. What is the day and time when precipitation will most likely occur at this location? Monday at 6 a.m., Monday at 8 p.m., Tuesday at 8 a.m., and Tuesday at 6 p.m. So how do I do this? Well, I go back to the chart and I look at Monday at 6 a.m. and I make a line going up. I go Monday at 8 p.m. and I make a line that goes up. Okay. I go Tuesday at 8 a.m. I make a line that goes up. And then I go Tuesday at 6 p.m. and I make a line that goes up. Okay. So here's the thing. I see two answers that look very similar in terms of the dew point and the air temperature. Like this answer and this answer, or this answer 6 a.m. and this answer, they look very similar. So they can't be both correct, which means that I would want to immediately assume that both of those are incorrect because if one were true, the other one would also be true. So something about the other ones would actually make more sense that one of those would be the answers. And if I look at the 8 a.m., now this is me using test taking strategy. If I look at the 8 a.m. time on Tuesday, this one also looks a little bit like the other two times that I said were probably incorrect, right? Versus this one seems like there's something special going on. This is just test taking strategy. I strongly suspect that this one's incorrect, which is making me think that that one is the correct one. So let's actually talk about though why any of these would be correct. When is precipitation most likely to occur? Okay, this precipitation is most likely to occur when the dew point equals the temperature this actually implies that droplets can form. Okay, so if you actually look at the reference table, let's go to the reference table where I talked about dew point. Here we go. You know that when it rains, it tends to be very humid. And if you look for where it's very humid, 100% humidity, all of them are on this column. And that happens where the difference in between the wet bulb and dry bulb temperatures is 0. So that's where the humidity is highest. Are there other points where the humidity is highest? Well, if the difference is like 1 and the temperature, the dry bulb temperature is higher. Now, the lower the point is, the lower the difference between the wet bulb and dry bulb temperature, the more likely there is to be precipitation. Okay, so the most likely time is definitely that Monday at 8 p.m. Does it have to be that the difference in dew point and air temperature is exactly 0 for there to be precipitation? Well, no, not necessarily. Only because the difference in dew point and air temperature on the surface of the Earth could be one thing, but if you climb up to where the clouds are, the air temperature and dew point could be different. Usually, when you go up a little higher, usually the air gets colder, uh, which and if the dew point, if the humidity doesn't go down, so then the dew point stays the same. So as you go up, the air temperature goes down, which the dew point stays the same. So the difference in air temperature and dew point goes closer to 0, which allows clouds to form, which allows precipitation to happen up there, which eventually hits us right here. So, but again, usually rain only happens when those are close to each other on the surface. All right, that said, numero 20, number 20. The photograph below shows a portion of the Grand Teton Mountains on a mid-July day. The inset map of the United States shows the location of the Grand Tetons. Okay, that's around right there. Well, it's on the west coast, close to is it in Yellowstone or close to Yellowstone? I actually don't know the answer to that. But again, if you know the answer, please do mention it. Which factor is responsible for the snow seen on these mountains in July? So they told us it's July. We are not used to seeing very much snow in July. Snow in July. And notice on these mountains, on the mountains in July. Okay? Let's see. Elevation, longitude, latitude, or steep slopes. Okay. So I'm going to immediately eliminate some answers that don't make sense for me. Steep slopes have no effect on snow. In fact, you could see there's plenty of crags here where the steep slopes have no snow, and then where it gets flatter has some snow, right? So, and there's also plenty of mountains that don't have snow on them. And of course, also lower down, like if you actually make a line, there is a little bit of snow here, right? There's a little bit of snow here, and then there's snow all over here. A tiny snow, and little bits of snow here, right? But you see all the snow is higher up. So steep slopes, again, steep slopes have no effect on snow. Latitude, we are in the United States. So latitude in July is a hot month. Everywhere in the United States, July is a hot month, except for in some small places. Clearly, this mountain is cold enough to have snow. So there's got to be something about the mountain that makes it to be the snowy place. So it can't be latitude. Then elevation and longitude. Longitude has no direct effect on snow. This would be like literally longitude has no effect on snow. All right. So how about elevation? Actually, we see higher up in the mountain, there's snow. So, and that's actually what it is. Let's just acknowledge one thing that we do need to know. The higher up we go, we are in the troposphere. The higher up we go in the troposphere, the colder the air gets. In fact, I invite you, if you're lucky enough to be on a flight anytime soon, and your plane happens to give you details about the flight, if you look at the temperature of the air through which the plane is flying, I didn't do that ever until my very last flight uh, from New Orleans. I was flying and I noticed that the temperature was given negative 50 degrees Celsius, negative 50 degrees Celsius, which is exceedingly low. It's less than negative 50 Fahrenheit. It's around negative 60 Fahrenheit. That is very cold. That's colder than any temperature I have personally ever experienced. So the as you go higher up in the troposphere, it gets colder. Okay, so elevation is definitely going to be the answer. Snow. Think about snow-capped mountains. Snow-capped mountains. The mountains are snow-capped, but the base of the mountains are not full of snow. Rarely, except maybe in winter, right? Okay. Número 21, number 21. Uh, which percentage of the radioactive potassium 40 in a sample will have decayed in 2.6 times 10 to the ninth year? 25%, 50%, 75%, or 100%. So we do need to know the half-life of potassium 40. Okay, so do I expect you to know the half-life of potassium 40? No. Do I expect you to know to go to the reference table? Yes. So here's some radioactive decay data brought to you by the lovely reference table. Okay. Place this here and then scroll down so you can see it a little better. Okay. So if you look at the radioactive decay of potassium 40, we do need this because if we don't go here, we can make a lot of false assumptions. So the half-life is 1.3 times 10 to the ninth year. And this is 2.6 times 10 to the ninth year. This is actually 2 half-lives. So it's got to be the answer is less than 50%. Now, I got caught when I was doing this practice. I got caught remains. Okay? Less than 50% remains, which means greater than 50% decays. Okay? And why I got caught in this problem, I actually accidentally replaced the word. I didn't look back at the problem. In other words, I did a thing that students who are taking this test do, which is they look at the reference table, they get their answer, then don't go back to the question to see which question they actually asked. This problem could have asked how much of it decayed. They could have asked how much of it remains. And neither one is a trick question. It's not a trick question. They're asking the same thing in 2 different words. They asked how much of it decayed. Okay? So how much of it decayed? Less than 50%. I'm sorry, more than 50%. So the answer, we could cross out 25% and cross out 50% with 100% certainty. And so we're either left with 75% or 100%. Okay? Now, I strongly suspect that 100% is not the answer because of the half-life being so large. I just happen to know that 2 half-lives occurred. And there is a large misconception that if half of it decays in a half-life, then what happens in the second half-life? It's not that the rest of it does, because that's not a thing. It's actually half of what remains. Half of what remains decays. And 0.5 decays in the first half-life. So, well, actually, we have to do the math. Let's do the math real quick. So 2.6 times 10 to the ninth divided by 1.3 times 10 to the ninth, which is the half-life, right? The 10 to the ninth crosses out, and you can go to your calculator and do 2.6 divided by 1.3, and you get 2 half-lives. So how much decays? Is equal to 0.50 which decays during the first half-life, times another 0.50, which decays, how much remains, I'm sorry, how much remains is what I'm calculating. Because the half-life tells you how much remains. So, or equivalently, you could have said 0.50 to the power of 2, because that's how many half-lives occurred. Okay, 2 half-lives, 2 half-lives. Okay, and we get 0.25 remains. And you see that 25% is right there waiting for students. So that means 0.75 decayed. And that's the answer to the question. Okay? A lot of students get caught on that. Okay. Now, based on Earth's, number 22, number 22, based on Earth's geologic history, which group of organisms has existed for the shortest amount of times? Grasses, dinosaurs, birds, or humans? Now, I made the silly mistake of not reading the whole question before I started researching it. Yes, excuse me, this does appear in the reference table. So let's go to the reference table, page 8 and 9. Okay. Let's see, page 8 and 9. It's the combination of page 8 and 9. This doesn't show page 8 and 9 next to each other, but you know, there's here trilobites, nautiloids, ammonoids, crinoids, and I started looking at all these birds here, you know, and I started looking, and then I finally got to number 4, humans. And I know there's a certain thing about humans that I know. This one says which one has existed for the shortest amount of time. To me, it's so insane that the Earth has existed for such a long time, but humans have been around for such a short time. Humans have been around for about 100,000 years. From anatomical modern humans, but they had to. Anatomical modern humans looked a lot like we do now, but very much like we do now. So that, like, if you somehow teleported a modern human from back in the day and teleported them here, you might see similarities between them and, you know, some people that are around now, but there are differences. They still had a bit of a thicker brow ridge. They had that strong chin that we have, but there were some other differences that you might be able to notice. However, we did evolve from them, so some differences that we have within ourselves now just kind of evolved after. So that said, birds. I mean, had I just looked at it, I mean, again, go to the reference table. I'm not going to look at all of these because there's a lot of them. Birds. Now let's see if I could change the view, 2-page view. Ugh, it's still not showing me next to each other. So birds, so I'm just going to go back to the 1-page view. So birds, for example, there's this line that says 119 million years, right here, this line. And if you have the reference table, these 2 pages are next to each other. I'm going to show you real quick. These 2 pages are next to each other. So you are able to go to where birds are, right around here, and right around here, and go across to this side to see how long ago that was. But I'm going to have to do that with the reference table. This is the 4th line over here. 1, 2, 3, 4. Go across here about 146 million years ago. So obviously birds were around. Birds do descend from dinosaurs. This table shows like dinosaurs going extinct, but the true correct words when it comes to dinosaurs is that the non-avian dinosaurs went extinct upon the Chicxulub impact by an asteroid or comet. The non-avian dinosaurs. Birds are dinosaurs. They're avian dinosaurs. Okay. But anyway, the point is that they've been around for millions of years. In fact, all of these early-ish grasses started evolving during the time of dinosaurs, but true grasses um, did not start appearing until later. Okay, so there's a debate about whether dinosaurs ever ate grasses, and the debate is more because were grasses around when dinosaurs were around? And the answer for some seems to be no, and for others seems to be yes. I think by the time 10 years from now, we'll know for sure, and it'll probably be that yes, some early grasses were around. But either way, grasses have been around for millions of years, millions of years, millions of years, versus 100,000 years. Humans have been around for so much less time than any of these other animals. All right, número 23. And after número 23, number 23, we're going to actually start talking a little bit about snacks and things like that about the regions. So we're going to take a little bit of a break. So if you need a stretch break to put the phone down, stretch a little bit and things like that, please feel free to do that. But here, número 23, number 23, oxygen first became a major part of the Earth's atmosphere from the rifting of the Iapetus Ocean, rifting in the Iapetus Ocean, or life processes of cyanobacteria in the ocean, or extensive coal-forming forests, or the breakdown of ozone by ultraviolet radiation. Okay, so definitely pause and try to think about which one you think the answer is over here. So there's one that I want to just eliminate though. If I happen to remember when trees evolved, plants and animals and fungi actually, at least the evidence right now seems to imply that we all kind of appeared right around the same time, the Great Diversification event, about 540 million years ago. But trees, like big trees, started appearing a little bit after that. But if you notice, oxygen started appearing more than 2 billion years ago. Okay, so coal forming forests did not appear that early. Okay, so that one's not it. The first oxygen did not appear. The first oxygen really started appearing in the atmosphere, not due to any geologic event. It became a major part of Earth's atmosphere. This is biological. This is biogenic oxygen. That B looks like a modified D because that's exactly what it is. Biogenic oxygen. There we go. So that's where the vast majority of oxygen in the atmosphere came from. Why was it biogenic? Well, actually, any oxygen that appeared in the Earth's atmosphere for any reason tended to react with things. Oxygen is an extremely reactive molecule. Extremely reactive molecule. So much so that cyanobacteria appeared in on Earth, and they started creating oxygen. And it wasn't necessarily a big deal that they started creating oxygen because there were a bunch of chemicals out there that hadn't reacted with the oxygen. The reason they hadn't reacted with oxygen is that there wasn't any oxygen to react to. So, like, if you looked at the time at, like, let's say deposits of iron, you would see really shiny pieces of iron just kind of sitting there, unrusted, because there was no oxygen to rust them. But then cyanobacteria started making all this oxygen, but then the oxygen started being there were oxygen sinks around. And by the way, this is almost a lesson for us about human created carbon dioxide. And I'm going to talk about it, why that might be a lesson for us that we should take heed on. But the point is that the oxygen started reacting with other things. Why does that matter? Well, it turns out since oxygen is a highly reactive molecule, well, it actually was a damaging molecule to almost all living things. Remember, at the time before oxygen started being created by living things, diatomic oxygen O2, there wasn't any oxygen for them to use, so there wasn't anything around that learned how to use oxygen to survive. Once oxygen started being created, well, the oxygen would have a sink. It would literally just get reacted by some chemical out there and maybe sink to the bottom of the ocean, metal, rust the iron, create rust in other metals, and then that's it. But then all of these sources that could absorb oxygen eventually absorbed basically all of the oxygen that they could, and then suddenly the amount of oxygen in the atmosphere started blowing up. And when that started happening, remember that oxygen at the time for all living things was basically a poison. Well, things started getting poisoned. And literally, the creation of all this oxygen created itself a, a great dying. And uh, it was called the Great Oxygen Catastrophe. The Great Oxygen Catastrophe, literally, or the Great Oxygenation Event, or the Great Oxygen Catastrophe. Literally, things that were not used to having oxygen around started dying off because they literally started kind of getting reacted with the oxygen and getting broken down. So, um, even to this day, if you go put oxygen in places where there are living things, but there is no oxygen, if you throw oxygen there, the things that are living in there generally tends to die because they live in places where there is no oxygen and they prefer it that way. So it wasn't a natural process. Life process of cyanobacteria. Cyanobacteria are bacteria which undergo photosynthesis. Photosynthesis. And when they undergo photosynthesis, they create oxygen and also energy for themselves, which is great. Now, the breakdown of ozone by ultraviolet radiation, the reason that can't be it, one, there's not that much ozone in the atmosphere to begin with to create all of this oxygen. But the second reason is that in order to create ozone, you need oxygen. Ozone is created by taking oxygen and basically striking it with UV rays and lightning, and you create ozone that way. Uh, but you need the oxygen to start to be able to create the ozone and the ozone layer. So that can't be it. So the only one that makes sense is the cyanobacteria. And why there's a lesson for us here is, again, that living things at the time really had a chance of dying off completely because of all of this oxygen that was being produced. Life wouldn't have ended, but a lot of life did. I mean, it was an extinction level event. All the oxygen gathering in the Earth. The Great Oxygen Catastrophe was a true catastrophe on Earth. Why I'm saying that it may be a lesson. Well, for us, we are producing a lot of carbon dioxide and throwing it in the atmosphere, and we're producing global warming and a man-made global warming. We're doing that with carbon dioxide, but also methane. Uh, the thing is, though, the atmosphere, the Earth right now has a few sinks that are absorbing carbon dioxide. So we are not even fully aware of the entire effect that we could actually have on the atmosphere. One of the sinks that the Earth has is plants. It turns out the Earth is getting slightly greener. Why is the Earth getting slightly greener? Well, because there's more carbon dioxide in the air, and plants use carbon dioxide and light to create its energy source, which is sugars, and then they release oxygen. The amount of oxygen in the atmosphere is not increasing tremendously because the amount of carbon dioxide in the atmosphere is not, it's not proportionally huge. We're talking about 420-ish parts per million as opposed to like 21%, which is 21 parts per 100, or 210 parts per thousand, or 210,000 parts per million. 210,000 parts per million of oxygen uh, versus 400 parts per million of carbon dioxide. Um, but oxygen is not a greenhouse gas. Carbon dioxide is a major greenhouse gas. And once the sinks of carbon dioxide start to get maximized, meaning the earth can't get any greener, there is a limit to how green the earth can get. There's plenty of places where plants can't even grow, and there's plenty of places where the plants are already growing. So once the earth kind of reaches a maximum of how many plants it can grow, the carbon dioxide can actually start blowing up even faster, and we can actually get to a point where the amount of carbon dioxide we produce goes in a runaway uh, goes up in a as a runaway greenhouse effect. Not only that, there's places where methane gets used up. I mean, some living things do absorb methane, and it does get eliminated from the atmosphere little by little by just kind of rising up and out and going out of the atmosphere, but also sinking into the ocean and being used by living things, but very little and not in a normal way. But there's also the fact that we are releasing methane by the earth warming in the poles where methane was locked in ice. Now that those places are the permafrost is melting, the methane in the permafrost is being released, but also the plant matter that has been frozen for thousands of years is now getting unfrozen, and now it's being decayed by bacteria, and that bacteria is releasing methane. So we are actually arriving at a point where we may actually see a runaway greenhouse effect that hopefully we can stop through man-made ways. But if we get to a point where we can't stop it, we actually can get in trouble. So this is a lesson. Why is this a lesson? Because life created oxygen and was thriving right up until the point where it couldn't thrive due to the oxygen. Now we've benefited from the oxygen, of course, because we evolved from, bacteria, then complex life, and fish came from water and made four-legged creatures. Some of those four-legged creatures evolved to the great apes. Some of the great apes evolved to be humans, and now we are here. Uh, we breathe in oxygen, we breathe out carbon dioxide. So we definitely like the fact that there's a lot of oxygen. But if the sinks of carbon dioxide and methane go away or get maximized, we actually can get to a point where the carbon dioxide and methane concentrations in the atmosphere go way too fast, way too high, and maybe we can't do anything about it. So we really should take care of the earth and do our best to reduce the amount of methane released. That said, before we go to number 24, number 24, if you do want to skip over to that problem, go ahead, fast forward. But I want to talk about snacks and coffee. Okay. So before anything, what kind of snacks and coffee do you want to bring? You want to bring any snacks and coffee that don't affect your digestive system that hard. You could think about what kind of snacks that you've eaten in the past year that don't affect your belly too much. Even if you're not too lactose intolerant, I don't recommend bringing things that have plain milk that doesn't have lactase enzymes in it. So, like for example, you could put lactase enzymes in coffee. Well, I'm going to talk about coffee in a second. Or you could make coffee with lactase milk. I am a fan. This is a snack of Fairlife, and now none of these are sponsoring me, although they can contact me if they like. I'm a fan of Fairlife milk because they have a lot of protein and they have a little bit of carbs to give me a little bit of energy, just a little bit, and a little bit of fats to give me a little bit of energy. But they have a lot of protein in them, so they're actually a healthy snack. And they also they're lactose free, so they actually add lactase enzymes to break down the lactose, so they're lactose free. They shouldn't be giving you the bubble guts that milk can give you. Okay. The second thing I recommend as a eating snack is like a pure protein bar. Again, something that doesn't cause your digestive system to go haywire. It has 20 grams of protein, but it also has 18 grams of carbs, which gives you a little bit of energy, and 5 grams of fat, which also gives a little energy, but without destroying your digestive system. So I do recommend, if you need a solid snack, that's a good one, or a liquid snack, Fairlife milk is a good one. Any of those two companies want to contact me to sponsor, I would love it. Coffee. Uh, this is an important one to understand. You need to understand that coffee is a drug. Okay, and I'm gonna take a sip of my coffee here. Being Dominican, I was raised on coffee. Not every Dominican was raised on coffee though, and I was not like fed coffee as a kid. I'm not saying that, but I drank coffee in small amounts when I was a kid. I got to the point where I started drinking coffee during high school, um, for various reasons. So I was extremely accustomed to drinking coffee. So I brought that into the regions with me. Do understand though, being a drug, it can affect you in ways that's unexpected. You should not, if you are not a coffee drinker, meaning not I'm not talking about liking coffee. I'm talking about drinking coffee frequently. If you are not a frequent coffee drinker, you should not be bringing coffee to the regions. However, you could actually make decaf coffee, and decaf coffee does have caffeine in it. It's not caffeine free. Decaf coffee does have caffeine in it. The reason I recommend that, it actually, if you're not a coffee drinker, that little bit of caffeine that decaf coffee has in it will do wonders for you. Again, don't put regular cow's milk in it unless it has lactose. Unless it's lactose free, or you could put lactase powder in it, or you could actually break up a lactate pill and throw it in there. Lactate milk also sells, of course, lactose free milk. Uh, but if you're not a coffee drinker, you could bring decaf, and that's okay. The last thing I want to recommend is, look, I'm asthmatic. I bring my Weezer squeezer everywhere I go. Don't forget your meds, your Weezer squeezer, and any other meds that you're supposed to be taking. That if you actually take it during the regions, okay? I bring my Weezer squeezer. I have no shame in my asthma. I will take a puff in front of anybody. I'll take a puff on video. In fact, I've taken puffs on some of these regions videos this summer, because I'm not I'm not deleting anything from these videos. So that's what I highly recommend. Okay. And that said, on that note, I'm starting to get a little hungry, so I'm gonna have a sip of my Fairlife. I do appreciate any subscribes that I get from you guys. I'm trying to create the GOAT of all review videos. I really am. So if you feel like this is the GOAT of all review videos for the Earth Science, just let me know in the comments. Just say this is the GOAT. This video is the GOAT. But on that note, I want to hop over to numero 24, number 24. The letter X on the map shows the location of the present state of Florida on the early continent of North America. Okay. The region that is now Florida is inferred to have been positioned on the equator approximately, 59 million years ago, or 119 million years ago, or 232 million years ago, or 458 million years ago. So, if you know the answer to this question just because, look, thumbs up to you. Good job. I don't know the answer to this question just from the top of my head. There is one answer that I suspected to be wrong. The first one, 59 million years ago. That's after the asteroid strike that killed the dinosaurs. I say asteroid strike. Sometimes I read and they say it was an asteroid strike. Sometimes I read and they say it was a comet strike. The thing is that the difference between an asteroid and a comet is very subtle, and it has to do with activity of the nucleus, and there wasn't much activity once it hit the Earth, was there? Except there was activity on the Earth. So we actually have to go to the reference table and look for where Florida was on the equator. And if we look, I'm going to zoom in here. This is page 9, the table, and I see the equator right through the middle of the Earth, and I see Florida right here, 59 million years ago. It happened to be right below 30 degrees, and I see 119 million years ago. Florida was between 15 and 30 degrees, and about 232 million years ago, Florida was at the equator, almost touching Africa. In fact, if you notice, the shape of Africa right here and the shape of the United States here match. And the reason they matched is because they were literally touching at one point. Was there a small inland sea earlier than that? Well, this picture seems to imply that. I don't know. It may be that there was still water separating Africa and North America through a small sea, or I wouldn't call that a river. Um, but anyway, the point is 232 million years ago, Florida was thought to be right around the equator, 232 million years ago. So there is no elimination. There's no process of elimination. There is going to the reference table, seeing where Florida was on the equator, and it was on the equator 232 million years ago. Excuse me. Apologize for that. Let me drink some coffee here. While I scroll to numero 25, number 25, the division of geologic time into eras, periods, and epochs is based upon the appearance and extinction of life forms, occurrence of widespread volcanic eruptions, reversal in the Earth's magnetic field, or major mountain building events. Now, if you don't know anything about the epochs, this would be a difficult question to answer. So about the occurrence of widespread volcanic eruptions, this happens at various times. Okay. Okay. So this happens at various times, and they don't necessarily coincide with the geologic times and eras. The only special case is the Hadean eon, um, or the Hadean era, because that was the very beginning when the Earth formed. But that's not it. The reversal in Earth's magnetic field. This reversal of the Earth's magnetic field is not something we knew about. This is new info. I mean, it's almost all new info. Like, we didn't know about this like when George Washington was president. We some people had a little bit of a suspicion, but this is uh not something that we knew then. But the reversal in Earth's magnetic field is something that we discovered after we started defining the eras, periods, and epochs. So this is newer than the eras, periods, and epochs. And also, oops, let me scroll down here. There we go. And more frequent. The reversals of Earth's magnetic field happens on the order of like tens to hundreds of thousands of years, whereas the eras, periods, and epochs tend to be millions of years long. So choice 4, the major mountain building events. These are much less frequent. Much less frequent. For example, the mountains that the vast majority of of New York is in, those were formed in the realm of like 1.5 billion years ago. Billion. We've had a lot of eras, periods, and epochs between them. So that's not it. So it seems like the only one that seems to match the answer, maybe in principle, choice 2 might make sense, but actually, if we actually go to the reference table, this is a reference table question. So if let me zoom back to single page view. Oh, it didn't do it for me. The eras, periods, and epochs. So here are the eras, here are the periods, here are the epochs. And if you look for how these were defined, if you look, you look for where the life on Earth, where a certain life on Earth appeared. These all are divided by, and here is the one that said early grasses. Early grasses. Remember I said, did dinosaurs eat grasses? Yes or no? I got to zoom into this. Right now, there's a lot of data that says that grasses appeared after dinosaurs went extinct. So like 33.9 million years, whereas dinosaurs, the non-avian dinosaurs, went extinct 66 million years ago, or 65.5 million years ago. But there's some evidence that maybe there were some early precursors of grasses around the time, and then there's debate about whether those precursors of grasses should be called grasses or not. So definitional statements is the reason why there's a debate, not anything else. Okay, but the point is, all of these are, talk about which animals were around and which animals actually went extinct, and that's actually the thing that does it for us. It's actually which animals, generally speaking, went extinct. So this is what kind of does it. Because of this, by the way, there's a debate about whether we are in um, a new epoch. The Holocene epoch is largely dominated by humans spreading on Earth. And that's, notice that 0.01 million years, that's also known as, well, a million divided by times 0.01 is 10,000 years. Modern humans appeared about 100 million years ago, but we didn't spread. We didn't do most of our spreading until between 10 and 20,000 years, maybe even 30,000 years. The evidence is a little bit iffy at that point, but there's a question about whether we are in a new epoch, because of, since we define epochs based on the appearance and extinction of life on Earth, there's a lot of extinction going on right now, and it's due largely to human effects. So if we define it by the number of extinctions and the fact that we are in the middle of an extinction level event, are we in a new epoch, which would be called the Anthropocene? Anthro epoch. That is the name that people have been giving it, but it doesn't officially appear on everybody's lists yet. But that said, we are on numero 26, number 26. Numero 26, number 26. The first P wave from an earthquake was recorded at 10:20 and 00 a.m. at a seismic station located 2,200 kilometers from the earthquake's epicenter. At what time did the S waves arrive? Was it 10:12 and 0 seconds a.m., or 12:16 and 30 seconds a.m., or 12:23 and 30 seconds a.m., or 10:27 and 50 seconds a.m.? Now, I noticed that some of these are before 10:20 and 0 seconds a.m., and some of these are after 10:20 and 0 seconds. So it helps to know which waves travel faster, which waves travel slower. Okay, so I do happen to remember a little bit of details about the wave traveling speed. Why did I not mark the exact place on this? I did not mark the exact place, but it is on the reference table. Let's see. It's a table. Okay. Okay, so it's maybe in the beginning. I didn't mark the exact location of this. Okay. I didn't see it the first time I scrolled. Okay. Pressure. Oh, wow. I passed right by it. So it's page 11. Let me mark this in my notes. Again, I am not deleting any errors or anything like that on the video so that I don't have to do edits. Because the reason is, by the way, I noticed that the more edits that I do, it literally takes you like 4 to 5 times longer to edit than it does to actually record the video. So if I just don't edit, I could put more videos out. And I got 30,000 views on my videos, and I got requests for more videos. So I'm going to put out more videos, no edits. And that makes more sense to me. So I notice here the travel time for P waves and S waves are different. So if the P waves arrive, so if the S wave travel time is longer, that means the S wave travel time, the S wave speed is slower. But the point is, since the S wave travel time is longer, it's going to take longer for the S waves to arrive, which means that how long did the S waves take to arrive? Later than 10, 20, and 0 seconds a.m. Okay, which eliminates choice 1 and choice 2. And now we have a passing problem. Even if you don't know how to read this chart, now we have a passing problem. Let's actually get a screenshot of this chart so that we could write onto the chart itself. Okay. Okay. So the seismic station is located 2,200 kilometers from the earthquake's epicenter. So the bottom axis of this chart, epicenter distance. So I have to go to 2,200 kilometers. This is by times 10 to the third kilometers. So 2,200 is right there. So let me actually do this with a nice straight line, because this one I can do with a nice straight line. Okay. So I see that the P wave arrived at 10:20, and that one seems to cross right around this mark. And then the question is, when did the S wave arrive? Well, the S wave arrives at this after this amount of time. So the difference between those two is the amount of time that it takes for the wave to arrive. Now, I'm going to go back to my thing to see, because I know it's hard to make these lines perfectly line up. So I'm going to, because I got to move it just slightly. It's actually, because it's actually more accurate to say that it's around 8 minutes. Why is it not erasing? It's around 8 minutes. Okay. And then the other one is around 4 minutes and 20 seconds. Okay. So if you do 8:00 minus about 4 minutes and 20 seconds, so that's equal to 3 minutes and 40 seconds. So this is an estimate, so I know that they don't expect you to be so perfectly spot on. And in fact, if I had used the numbers that I had before, it would have still been okay. But if I use 3 minutes and 40 seconds, then I do 10, 20, and 00 a.m. plus 3 minutes and 40 seconds. I get 10 minutes, 10 o'clock and 23 and 40 a.m. And whichever answers closest to that is actually the answer, and that's got to be choice 3. So, 10 seconds here and there is not a big deal. You wouldn't have gotten the question wrong if you did a little bit above or below that answer. What I did, yes, the boxes are really very close to each other. So, but if you did really close to each other, you still would have gotten a very similar answer. Okay, maybe a little less than 30 seconds or a little more than 30 seconds, like I did. Whatever you would have gotten that. The big thing is, though, notice that you have to take into account how far away the station is for the S waves and the P waves. A lot of students might get that 8 minutes and add 8 minutes to 1020 and they get to 1028 plus or minus a few seconds. But they forgot that the P waves arrived later as well. So the P wave and S wave difference is what really matters about it. That said, número 27, which 2 hotspots are located at the plate boundaries? Iceland and Yellowstone, Tasman and St. Helena, or Canary Islands and Galapagos, or Easter Island and Bouvet. Now, this is a reference table one, but which one is located at the plate boundaries? I remember that Yellowstone is not located at the plate boundary. So even if I didn't know how to read a reference table, or didn't even think of going to the reference table, then I still could have gotten to 1 in 3 chance of getting it right. Not quite a passing problem, but that would help. So how do I do this problem? I literally have to go to the reference table, and I go to page 5. Okay, I got to rotate this a little bit. And I see hotspots. I see hotspots all over the place. The Yellowstone hotspot is quite far from the boundary. That's why I eliminated that one. So Iceland doesn't appear in any other choices, so I could eliminate choice 1, though. Let's go for these other ones. Let's see if we could find them. Tasman, St. Helena, Canary Islands, Galapagos, Easter Island, and Bouvet. We literally have to just find them. And we search around, and we see Tasman hotspot right here, not on the boundary. Now, if you were debating and saying, oh, but Yellowstone is kind of close to the boundary, well, then in that logic, so is Tasman. I mean, they're far. You can't go that way. It has to be on the boundary. So Tasman gets eliminated. Okay, so that one gets eliminated. So then Canary Islands, Galapagos, Easter Island, and Bouvet. Let's see. So the Iceland one is in Northern Europe. The Yellowstone is in the Western U.S. The Tasman was in Australia. St. Helena is actually south of Africa. The Canary Islands over here. Let's see if we find in Canary Islands, Galapagos, or Pacific or Nazca. The Canary Island one is in North Africa, north of Africa, North Africa. So in the ocean, Canary Islands. But notice that it's actually far. It's a little bit far from the plate boundary, although it's closer to the plate boundary. So that one's not it. Uh, cross that one out. And the Galapagos is actually not either. But now Easter Island and Bouvet. Let's just confirm here. Easter Island and Bouvet. Easter Island is in the Pacific Nazca Plate boundary. Easter Island, bam, look at that. Can you debate whether that is on the boundary or not? I mean, if you were debating whether the other ones were or were not on the boundary because they're kind of close or not, fine, just keep going with the rest of the choices. Test taking strategy, analyze the other ones. Because if you're debating whether the other ones are near the boundary enough or not, well, and then you just guess, that's not a good strategy. More likely, a better strategy is to find the other ones and see if those match. Oh, the Galapagos hotspot is on the boundary, but then the other one wasn't. So on that choice, but Easter Island hotspot is right on a boundary, and the Bouvet uh, hotspot in the very South Atlantic, right on the boundary. I mean, literally on the boundary. So that one is undebatably, these two are undebatably in the Pacific Nazca boundary, and the Bouvet is on in the very South Atlantic. Again, um, in the African and Antarctic boundary. So that is the answer. That's literally just a reference table problem. And we move on to número 28, number 28. If you do feel like this video has been helpful so far, there's your hint. I do appreciate that subscription. That said, number 28, número 28, a block diagram below shows a portion of a meandering stream. A meandering stream. Points A, B, C, and D, A, B, C, and D are locations on the stream bed. The arrows show the direction of stream flow. Okay, so at which location is the greatest amount of deposition most likely occurring? So A, B, C, or D. Deposition means dropping of sand, silt, and pebbles, and etc. Okay, so this one's not. I mean, if you don't know anything about streams, well, then you're kind of stuck at this one. But this one is again your. It takes your knowledge of living environment. Oh, I'm sorry, your knowledge of earth science to be able to answer this question. One important detail is though that streams meander more over time. Streams don't get straighter, they actually start waving, meandering more over time. So, what is a meander? Meander is a bend in a stream. One of out of all people, Albert Einstein wrote a paper on meandering streams. Um, so he wrote a lot of things. He's a smart dude. So being that they bend or meander more over time, which would cause a bigger bend. A bigger bend would be caused by this bend over here becoming bigger, which means that more deposition would happen here, and then more erosion would happen here. And that might be surprising, because you might say, oh, well, the bend pushes water that way, so that's where the water would deposit its pebbles, silt, sand, and etc. But in fact, it's the other way around. The moving water actually drags more away, and you see this hill with these weird lines. That's actually caused by small sand falls, so or erosion. So as the river takes more dirt, the sand or silt or rock or soil falls into the river and more of it gets dragged away. So that actually on the outside of a bend is where the erosion happens, and on the inside of the bend is where deposition occurs. So the answer to the question, where does more deposition occur? It's definitely going to be C. Okay. On that note, we go to número 29, number 29. Okay. Instruments that record seismic waves on Mars allow scientists to infer the gravitational forces between Mars and its two moons, or percentage of the minerals in the crust of Mars, or availability of surface water on Mars, or internal structure of Mars. As I said, highly recommend pausing the video and making a choice on this question, because you know, if you do it that way, and again, if your regents is tomorrow and you might, or even in a couple hours, you might be debating, is it better to watch more of the video, or is it better to choose a question and then see what I say about it? It's actually better to to make a choice on what you think the answer is, and then see what I say about it afterwards, instead of, let's say, watching the whole video, uh, in terms of your maximizing your grade. So, seismic waves on Mars to infer the gravitational force between Mars and its two new moons. So, its two moons. This force of gravity is equal to this. You don't need to know this formula, but G m1 m2 over r12 squared. So the force between uh, Mars and its two moons literally can be inferred by the size of Mars and the fact that we know them by a good amount, the mass of Mars, and literally the size of its moons. That's because we also know what the moons are basically made of. So uh, that's not that. So the instruments recording the seismic waves tells us nothing about the gravity between Mars and its moons. So choice two, the percentage of minerals in the crust of Mars. Well, that again, the seismic waves don't tell us about the mineral content. Okay, so that's not quite right. The next one, availability of surface water on Mars. Perhaps the seismic waves can tell us about the internal water on Mars, but not the surface water. So that's why we cross out this one. So that one we can eliminate right away. Now we have a passing problem because we've eliminated two choices. Uh, how about this one? The internal structure of Mars. Actually, so the seismic waves kind of act kind of like a sonogram, which is pretty cool. The seismic waves kind of act a bit like a sonogram. So if we listen to an earthquake and how the earthquake propagates through Mars, it actually acts a little bit like a sonogram, and we actually can infer a lot of information about the interior structure of Mars. So that one uh, actually would is definitely very much a correct answer. Okay. Numero 30, number 30. The block diagram below represents a landscape with two valleys, and I do make a quick look at it. Mountains, valley, and valley. Igneous rock, shale, limestone, sandstone, conglomerate, shale. Okay, great. And then I go back to the problem. The two valleys most likely formed because the shale and limestone bedrock are less resistant to weathering than igneous sandstone and conglomerate bedrock, or are more resistant to the weathering than igneous sandstone and conglomerate bedrock, or have undergone shorter periods of weathering than the igneous sandstone and conglomerate bedrock, or have undergone longer periods of weathering than igneous sandstone and conglomerate bedrock. So this one is not a 2x2 question, although there is a two-ness. Uh, there is almost like a two-ness by 2x2-ness because the first two have the same type of stones, and the second, well, I guess it is a 2x2. Yes, it is a 2x2 because it's less or more, and then it's resistance versus weathering time. So yes, that is 2x2. But the fact that these are opposites means that we can actually compare them to each other. Like choice 3 and 4 are opposites of each other. Choice 1 and 2 are opposites of each other. So maybe something about them can give us hints as to which one makes most sense. Now, if I see the location of the stones, I see that they actually curve up and they all meet at the surface. They curve up and they all meet at the surface. So the fact that they all meet at the surface means that they actually have undergone just about the same amount of time of weathering time as each other. So choice 3 and 4 could be eliminated because these two, they're next to each other. So the layers are next to each other. Above ground, horizontally, which implies they've undergone about the same amount of weathering time. So we could eliminate choice 3 and 4. Now, how about this? Are the valleys because the shale and limestone are less resistant than the other ones or more resistant to the other ones? Okay, so now if they undergone the same amount of weathering, then the ones that are weathered more are going to be lower. So weathered more, oops. So weathered more, that means that they're going to create valleys. Okay? And uh, uh, actually, we shouldn't say weathered more because that can imply uh, so how about less weather resistance? Less weather resistant. So less weather resistant implies that you get a valley, and more weather resistant would imply that you get kind of a hill or a mountain. So let's see. So that means that the sandstone. So which one do we want to compare? The shale is more weather resistant or less weather resistant? Shale and limestone. The shale is at a valley. The limestone is at a valley, and the shale is at a valley, which means that they're less weather resistant. Okay? So the shale and limestone are less resistant to weather. Not more resistant. So the answer to this one is choice 1. Nice. So that one is a really important question because we do have to know, yes, it is true that layers tend to form from at the top. The layers tend to form at the top, and then more layers tend to be formed above them. That's not 100% the case, but it is the case most of the time. And then there's also things like clearly the layers can get twisted and turned so that they're kind of sideways now, and then the top actually is a series of layers that were formed at different times, or they can even get completely inverted so that the layers were formed in the reverse order. So there's a lot of ways that layers can be formed. Okay. So, but they tend to be formed on top, and then the next layer gets formed on top, and the next layer gets formed on top, kind of like you're building a cake from the bottom up. So the bottom layer is the oldest, and the top layer is the youngest. And then you do something to them. Maybe delete a layer, maybe turn the whole cake, maybe flip over the cake, all that stuff. Okay, which is the same thing that happens to rocks. Okay, number 31, número 31. The photograph below shows rocks found in England. I see a hammer, which tells us the size of the rocks. Okay, it's really hard to tell how big the rocks are unless you have something to compare to. Which process most likely caused these rocks to become smooth and round over time? Abrasion in moving water or dragging by a glacier or sandblasting by wind or downward movement by gravity. Okay, so let's see. These, if you happen to do any landscaping, these look like river rocks. That if you happen to ever had some landscaping done, river rocks tend to be nice and smooth. So anything that talks about water is I'm liking. So I'm liking these this answer right over here. Now, dragging by glaciers, sandblasting by wind, or downward movement by gravity. Well, um, if they're dragged by a glacier, this tends to produce jagged rocks, jagged boulders, and also sand deposition. So if you go to Long Island, for example, I grew up in Long Island. You go to the beaches in Long Island. The beaches in Long Island were basically deposited by glaciers. In fact, Long Island itself was deposited by glaciers. I was speaking to someone in Canada who was telling me that those lakes were formed. A certain lake was formed like 50 million years ago by retreating glaciers, and I was like 50 million years ago because it messed with my brain because retreating glacier 50 million years ago. But the thing is that it's a different place, much further north in Canada, uh, where I was. That makes sense. Though as the glaciers retreated, they retreated much later in Canada. Uh, but so the glaciers that formed those lakes were happened at a much earlier time. Um, Whereas Long Island itself, you could actually see there's two streaks that cross Long Island of just depositions made by glaciers. Literally, the glaciers came down to where Long Island is, deposited half of Long Island. The glaciers retreated, and then they formed again and deposited another part of Long Island. And then literally, so Long Island was literally deposited there, oh, about 20 to 30,000 years ago. So Long Island is not a very old island at all, whereas these islands these islands that she was talking about were formed like 50 million years ago, which I thought was really cool. Yes, the islands were formed because the lakes themselves were actually dug out. Okay, that said, so this one doesn't make sense because of what glaciers do. The sandblasting by wind, this is weathering, but it happens too slowly. But it also it just erodes. It just erodes very slowly, but it doesn't actually round rocks all the way around. See, these rocks to be rounded all the way around would have to tumble, and the air just doesn't tumble rocks like that for it to happen so quickly. And the downward movement by gravity, it just doesn't really weather rocks much. Not much. It doesn't weather the rocks much. It transforms the rocks perhaps after it's gone some downward movement for long enough after many eons, but then it transforms the entirety of the rock layer, not like individual pebbles into round pebbles. So the abrasion by in moving water is actually the one that makes the most sense. The rocks would have to tumble. The sand literally flowing over the rocks causes rock abrasion and rounds out the rocks that way too. Okay, número 32, number 32. Another photograph with a mountain with snow on top. The photograph below shows a volcanic mountain. Which map best shows the most likely complete stream drainage pattern near the summit or top of this mountain at the time of this photograph? Is it choice 1, 2, 3, or 4? Now, you can debate this one as much as you want, but you kind of have to know how water flows, and that's kind of what this one's asking you to do. Do you know how water flows? Water, being that it is pushed around by gravity, flows downward, down a mountain, down a mountain, down a mountain. So that means that the water probably flows that way, flows down here that way, flows down that way, and now the maybe flows down that way. It flows down the mountain away from the peak. And the ones that flow away from the peak, well, this one seems to flow away from the peak. This one goes somehow across the peak. Literally going up the peak to go over to go back down. Rivers don't go upriver. Rivers don't go up; they go down. So this one can't be it. This one also can't be it. This one goes across the peak. Now we're left with choice one and choice three, and I guess you could sit and debate whether choice one makes sense or not. And I would get why you might think that choice one makes sense. Like if you have the peak right here, this is a volcano, so maybe you have a little bit of water flowing towards the center. This is the problem though with choice one. Choice one has these rivers flowing kind of around the peak, which means that it's not flowing downward, it's flowing in a circular direction. So this one doesn't make sense. The rivers would have to flow down the peak. So we'd have to cross that one out. This one goes down away from the peak. So this is the one that makes the most amount of sense. Definitely that one, okay? All right. So again, the drainage pattern has to be away from the peak because water runs downhill. Okay? Now, número 33, number 33, yet another river problem. But now this one's at the end of a river with an ocean appearing here. This looks like it was taken from a plane. When you fly over land with a plane, it actually looks really cool. I would recommend looking down and seeing what the ocean looks like, seeing what the land around the ocean looks like, seeing what the land itself looks like. It's really fun. I know flying around in wintertime, you actually see the lake effect snow, but you also see that snow on one side of a river tends to be greater than snow on the other side of the river because the air literally flows over the river, picks up warmer, wetter air, and basically immediately cools down and comes down as snow. So a small amount of snow that lands on the ground is actually just due to rivers and lakes, small lakes. But then, of course, there's the lake effect snow, which is due to the giant lakes like the Great Lakes. That's why, for example, places like Rochester Rochester and um, Albany get a lot of snow. And Buffalo, I was thinking about the city Buffalo. Buffalo also gets a lot of snow, and Syracuse due to lake effect snow. Anyway, number 33, numero 33, the aerial photograph below shows a landscape feature. This landscape feature is it a landslide formed by mass movement, or a landslide formed by stream deposition, or a delta formed by mass movement, or a delta formed by stream deposition? So we do have to know, this is again, it does take our knowledge of earth science. Um, they do tell us at least that that's an ocean, okay? And so we have to know what's going on here. This is a river, okay? That's a river. I have to change colors because even though I could see this red as looking bright, fortunately, I know that a lot of you are colorblind, like I am. I actually am colorblind, so you may not see that. But this one, which varies in color, might be easier to see. Okay, this is an ocean. This is a river. That's a little bit hard to see for me too, but because it varies in color, at least we could do a little bit of differentiation of the colors, and they're also not the colorblind mean colors. So that's a river, and so this is a deposition. Okay, so this is a delta. This is not a landslide. It's not a landslide. A landslide is when land slides down a hill or a mountain. So it's not a landslide. This is a delta. Now, is it formed by mass movement or is it formed by stream deposition? The question, you might debate whether it's mass movement or stream deposition. After all, for stream deposition to occur, mass has to be moved. But the question is referring instead to, is the mass moving all by itself, or is it moving, or is it being deposited by the stream? And in fact, it's not moving all by itself. It's moving, it's a sand and silt floating in the water in the river, that once the river reaches the ocean, since the river since the water speed decreases, the larger particles can be deposited. And so that's actually what's happening. A stream is depositing its sand and silt. So it's a delta formed by stream deposition. Número 34, number 34. What is the name and texture of a sedimentary rock composed of carbon? Shale with a clastic texture, shale with a bioclastic texture, or bituminous coal with a clastic texture, or bituminous coal with a bioclastic texture. Okay. So all of these say somehow clastic. Bioclastic versus clastic. So it's important for us to know what clastic means. Well, it helps to know what clastic means, although it's not an absolute requirement. Clastic means fragmented. So bioclastic is fragmental, but also biogenic. Now you might say biogenic can't be a texture, but the point is fragmental texture that's not biogenic. It looks like a certain way, whereas the fragmental texture, which is formed by living things, feels actually and looks at texture wise looks different. So bioclastic makes more sense if I had to choose one from this multiple choice, but it's not necessarily um, obvious based on this. So if we go to page 7 on the reference table, okay. So let's read this again. Sedimentary rock composed of carbon. So if we go and look, so here shale is mostly composed of quartz and feldspar and other minerals. Okay. So I'm going to put quartz in blue here. Quartz, feldspar, etc. Okay. Whereas bituminous coal, if you see all the composition here, is we're looking for carbon, composed of carbon. Now we have bioclastic. Bioclastic. This is, and here we have the rock name bituminous coal. So it is on the reference table. Let me take a screenshot of this to add it to this document. Oh, it took the words with it. Okay, so bioclastic, bituminous coal, carbon. So that matches that, but it also doesn't match the clastic, it matches the bioclastic. So it is choice 4. It is a reference table question. A lot of these questions end up being reference table questions. In fact, the very next question, Número 35, number 35, is also a reference table question. The cross-section below represents an igneous intrusion into sedimentary bedrock layers. Okay, so you might be scared the moment you see that, but it does say that this is an igneous intrusion, and it says into sedimentary bedrock layers. And we have sedimentary bedrock layers here. Letter A, B, and C identify different rocks within the shaded zone of contact metamorphism. Contact metamorphism. Okay. Which metamorphic rocks are most likely formed in zones A, B, and C? And then, so they have letters for A, B, and C. So how do we, I mean, marble for A, marble or metaconglomerate. For B, is it gneiss or quartzite or schist? and C schist or metaconglomerate or marble or gneiss. So this is yet another reference table question. And we look for in the diagram, we look for marble, limestone, sandstone. Okay, where are we looking? Hold on, give me a second. The last column to the bottom, third to last column. Okay, so this, oh, here it is, the metamorphism. So we're looking for the metamorphism. So the limestone, this over here, let's actually take a screenshot so we can actually bring it over. We're looking for the metamorphic rock identification here. Okay, so the top one is limestone. Now, how do I know that? Because of the picture on the top, actually. So maybe I should take this one too. Let's bring that over here. So we got limestone here. We got sandstone here. Over here, sandstone. We got limestone there. And over here, we have conglomerate. That's over here. So now we have to see what those get transformed into. Let's see. The conglomerate gets transformed into, let's see, conglomerate gets transformed. Is pebbles maybe distorted or stretched? Where is it? Regional or contact? Various minerals. Various minerals right here, which means that it's it's a conglomerate. So this gets transformed into meta conglomerate. Whereas the sandstone, what does that get transformed from or into? The sandstone, if you see this metamorphism of quartz sandstone, that gets transformed into quartzite. And then finally, the limestone, what does that get transformed into? The limestone get transformed into, well, metamorphism of limestone or dolostone gets transformed into marble. So again, various minerals, limestone, and what was the other one? Limestone. Where did the limestone go? Oh, that was the limestone. And then the sandstone. Sandstone. Those are the three that we're looking at. So the answers are that A is marble. Maybe crossing out those. B is quartzite. And then C is the metaconglomerate. The only one with 3 check boxes is choice 2. That one maybe for me was the hardest one to kind of look up, especially the metaconglomerate one. However, if you couldn't find that one, which you saw that I had a little bit of struggles because I didn't make a note of it. If you notice there that you couldn't find that one, still, if you just looked at the first two, letter A and letter B, letter E got transformed from marble. I'm sorry, from limestone into marble, which eliminates choice 3 and 4, leaving choice 1 and 2. And then the sandstone in B got transformed into quartzite, which eliminates, which keeps choice 2 and 3, but eliminates choice 1 and 4. The only one that's left after A and B is choice 2. So even if you couldn't find the metaconglomerate, you still had choice 2. Okay? So that's on the test taking strategy side. And from there, we go to part B1. Now, the parts of this test, they're actually all very similar. Some of them require more of the reference table, some of them require less of the reference table. So that's the only difference. But there are also questions that sometimes require um, more, like the different parts uh, might be like a two-part question. Like this one, 36 and 37 use the same diagram. Número 36, number 36, we have to read the top. Base your answer on 36 to 37 on the diagram below and on your knowledge of Earth science. Yes, we do have to read the top because it tells us what it is. The diagram represents the predicted collision between the Milky Way and its sister galaxy, the Andromeda. The collision is predicted to begin in about 4 billion years. It will take an additional 2 billion years to completely merge these two galaxies into one galaxy, which they're going to call Milkomeda, supposedly. Well, we'll see. We'll see them. Collisions in collision scenario for the Milky Way and Andromeda galaxies. So they're going towards each other and meeting somewhere in the center. Andromeda is actually slightly more massive than the Milky Way, so it's not technically coming towards us. We're technically going towards it, and we're meeting at a common midpoint. Anyway, so number 36, número 36, the gravitational force pulling the galaxies together is influenced by the mass of the stars and the amount of cosmic background radiation, or mass of all the stars and the distance between the two galaxies, or the age of the stars and the amount of cosmic background radiation, or the age of the stars and the distance between the two galaxies. Now, I would love it if this reference table had a formula for the way gravity works, but it doesn't. But the way gravity works, the force of gravity is equal to some constant. This is the gravitational constant. It's some number that exists to make the formula works, times the mass of object 1, let's say Milky Way, times the mass of object 2, say Andromeda, divided by their distance squared. So that's it. That's it. The gravitational force is not affected by anything else. So the gravitational force is pulling on the galaxies together by the mass of all the stars. Yes, that makes sense. The mass of the stars, the ages of the stars. Nowhere here says, oh, but this star is heavier than the other. No, the ages of the stars doesn't matter. So we could eliminate choice 3 and 4. And then the second one choice is the amount of cosmic background radiation or the distance between the two galaxies. Nothing in this formula contains a radiation term or factor, but the distance between those two is definitely in the denominator. So choice 2 is the one that makes the most sense. Choice 1 doesn't make sense. Okay. Yes, clearly we've brought up this formula twice already. So you do have to know how gravity works. Gravity is affected by the mass of two objects and the distance between the two objects. The Earth, you're stuck on the Earth because the Earth and you are pulling on each other by equal and opposite forces. So that weight that you feel is literally the Earth pulling on you. Número 37, number 37. The Andromeda galaxy has a shape that is similar to the Milky Way galaxy. The shape of the Andromeda galaxy is best described as elliptical and is the only other galaxy in the universe, or elliptical and is one of the billion other galaxies in the universe, or spiral and is the only other galaxy in the universe, or is spiral and is one of billions of other galaxies in the universe. Fun fact, even at the point of Albert Einstein, we didn't know that there were other galaxies. Yes, by the time Albert Einstein was working on the A bomb, he knew that other galaxies existed. But when he first started in publishing those miracle papers, he didn't know because no one did. So, I mean, we had reason to suspect that maybe there was more matter, but as far as we knew, that this was it. So, and being as smart as he is, maybe he thought maybe there's a chance. I don't know. But that said, now we know that there's billions of galaxies. Okay, and so the fact that it's the only other galaxy, we should actually know just by reading science articles that there's many other galaxies in the universe. So we cross out the ones that say the only other galaxy in the universe. And when they say billions, it's actually in the realm of billions. It's about 200 billion to 2 trillion galaxies. That's an enormous number. For some reason, for me, it's like less than I expected, but it's still an enormous number. There's like 7 billion people in the Earth as of the making of this video. So for every person, there's maybe 30 galaxies. Okay, so now the thing is though the shape. You have to know the difference between an elliptical galaxy and a spiral galaxy, and it helps to know that since it's a similar shape that's similar to the Milky Way, it helps to know that the Milky Way is a spiral galaxy with 2 big arms, and the Milky Way happens to have 2 small arms. And we're kind of close to one of the smaller arms right now, the Earth within the Milky Way. So spiral is the one that makes sense. Now, when the two merge, they will merge and form an elliptical galaxy, most likely. But right now, they are spiral. Okay. The reason they're likely going to form an elliptical galaxy is that they are not coming next to each other like this and colliding like this. They're colliding kind of like this. So since you have some orbiting this way and some orbiting in this plane, they're going to collide and have stars orbiting in a lot of different ways. So it'll be a very chaotic galaxy at that point. But interestingly, most likely, the Earth and Sun, whatever states the Sun is going to be at that point, will probably survive because there's going to be very few stellar collisions. All right, number 38 through 40, número 38 a 40. Base your answers to number 38 to 40 on the diagram below and your knowledge of Earth science. The diagram represents the water cycle. Letters A through C identify some processes. Okay, so I do look real quick. I see A, arrow pointing up, arrow pointing down, C, an arrow pointing down here, and B, arrow pointing up. And then the arrows represent movement of water. Movement of water. So water going up, water going downhill, water going up. Okay, so número 38, number 38. Which process is represented by letter A? Transpiration, capillarity, infiltration, or precipitation. So I look at A, and water is going upward with not even visible, but water is going upward over the trees, as opposed to like letter B, water is going upward from the ocean. So A and B have to be different. Well, I mean, in a sense, different. They're both due to some sort of evaporation. So which one is it? So transpiration is equal to the evaporation of water from plants. So that one's looking really good. Whereas letter B, capillarity, is another word for capillary action, which is equal to the movement of water up a capillary. Up a capillary, not out of a capillary, just up the capillary. Okay? So that's one of the things that makes water go up a plant. But there's other things that make water go up a plant. And letter 3, infiltration. This is equal to the downward movement of water into soil. And precipitation is that's rain and snow. Well, let's add fog. Sure. As long as the fog sticks to things. Okay. But the only ones that A is representing not precipitation, not infiltration, not a downward movement of water, not capillarity, because the water is leaving the plant. So transpiration is the only one that's left. Evaporation from plants makes sense. So número 39, number 39, which process and heat energy exchange are represented by letter B? Letter B, process and heat energy exchange. Heat energy exchange and the process. Okay, so is it condensation and gain and release of 334 or 2,260 joule. Okay, so I'm gonna have to read the questions for those who are visually impaired. Choice one, condensation and a gain of 334 joules per gram, or condensation and a release of 2,260 joules per gram of energy, or evaporation and a gain of 2,260 joules per gram of energy, or evaporation and a release of 334 joules per gram of energy. So, excuse me. So if you look at reference table 1 on page 1, there is a heat energy gain and release when water changes phase. So let's actually add that to this screen. Okay. So at letter B, water is going from the ocean up. Condensation is water turning from gas to liquid, whereas evaporation is water turning from liquid to gas. So we could cross out the condensation choices because the water is actually turning from liquid in the ocean to gas in the air. So it's evaporation. Now the question is it a gain or release? Luckily, these are two different numbers, a gain of 2,260 joules per gram or a release of 334 joules per gram. Luckily, vaporization is the only one that matches here, because water is turning from liquid to gas. It's 2,260. So we could sit there and debate gain or release, but luckily we don't actually have to debate that. But it's because a release happens when a release of 334 joules per gram happens when freezing happens. Freezing and melting correspond to this energy exchange. Freeze, and when water freezes, it releases 334 joules per gram of energy, and when water melts, it absorbs 334 joules per gram. So, but when water evaporates, it actually gains energy, 1,260 joules per gram, which is the reason why evaporation cools things down. When things cool down, they that means that they lost energy. That's why when your hands are wet and you blow on them, they feel cooler because your hands got cooler because the water literally leached energy from your hands. Leached energy from your hands, leached energy from the air, evaporated, and the only molecules that remain in your hand are the cooler molecules. So evaporation, the water gains 2,260 joules per gram. Okay. Numero 40, number 40, which conditions would cause runoff at location C to decrease? So the runoff, this is the water going down the hill is the runoff. So which one would cause runoff to decrease? Decreased precipitation and decreased slope, or decreased precipitation and increased slope, or increased precipitation and decreased slope, or increased precipitation and increased slope? So I should say runoff. Well, yeah, okay. Let me not go there. Runoff, is it decreased precipitation? Well, if you have well, actually, I said decreased that runoff is just the water, but it actually, I think, is the nutrients as well. Nutrients, soil, I think that counts as runoff. If you can confirm, please post in the comments. But which one would cause the runoff to decrease? Notice again, this is a situation where they're asking us to compare one situation versus another. If you literally make it rain more, you will get more runoff, clearly. So if you increase precipitation, you get more runoff. If you decrease precipitation all the way down to zero, you get less runoff, definitely, to zero runoff. So decreased precipitation makes sense. Increased precipitation does not. So we could eliminate those, 3 and 4. And now a decreased slope versus an increased slope. Now this one might be a little bit harder. So, but if you think about what happens if you decrease the slope versus increase the slope, if you increase the slope, the water is just going to go run down as fast as possible. But if you decrease the slope, some of the water has more time to percolate. Or infiltrate. So if what that means is that a decreased slope decreases runoff. So whereas an increased slope increases runoff. The only one that has two checkboxes is choice 1. Choice 2 does not have two checkboxes, so choice 2 is incorrect. And that is number 40. Okay, so base your answers to 41 through 44 on the topographic map below, and on your knowledge of Earth science. Lines A and B and C, D are reference lines on the map. So I see from A to B, and I see crosses some lines, great. And C to D crosses some lines, great. Elevations are shown in feet. Letter X represents a location on Earth's surface. Letter X here, and I see A, B, C, and D. Okay, cool. And I see contour interval 100 feet. I see, okay, cool. And I see a little map here denoting length. So which profile represents the most likely shape of the land between locations A and B? The most likely shape of the land between locations A and B. So we see on location A and B, location A is between 1,000 feet and this line, which is 900 feet. Let me use this color again, 900 feet. This is 1,000 feet. And B, this is at 500 feet, so this next line would be 400 feet. This line would be 300 feet. So here from A to B, the elevation is dropping pretty fast. So if we have A to B, A to B, whatever happens, the elevation is dropping pretty fast, starting from this point to this point. So we expect something pretty steep in between, and maybe a little bit flat at A and at B. So the one that looks like that is the one that makes the most sense. We see that the elevation changes really quickly from this point to this point. So it does have to be steeper in the middle. This one, choice 4, implies that the elevation at A and B are the same. But at point A, that's between the line at 1,000 feet and the line at 900 feet. Whereas choice B is between the line of 300 feet and a lake. Okay? So choice B does not make sense. Okay? Now, I know that there are not numbers. No, let me not address that. So that one, but that one doesn't make sense. So I guess I do have to address that. There are not numbers at the lines to the right of the 500 feet, going from the 500-foot line to B. So yes, in theory, it is possible that these lines actually start going up again, and the 500 feet is actually a minimum, and then it goes back up to 600 and then 700 in principle. But to address that, we actually need more context clues, and we actually see that at points C-ish, and at this corner here, there's a pond. The water runs down a river, and then there's a lake here. Since there's not a lake at this point in between, this can't be a minimum, because water runs downhill. So this has to continue downhill. So this is downhill, which means that point B is in fact lower than that thick 500-foot line. So point B has to be lower, which means that choice 3 is the one that makes sense. There can't be a valley at point B. We've just eliminated this one. And of course, this one doesn't make sense because the elevation from point A goes down from 900 and something foot to 500 feet. So that one can't work, and neither does this one. So that's why choice 1 was eliminated, and choice 3 is the only one that makes sense at that point. How about número 42, number 42? What is the approximate gradient in feet per mile from point C to point D on the map? the approximate gradient from point C to point D. Yes, it's true that from point C to point D, it goes really fast later on, but really slow early on. However, we're talking about the average. So we only have to know the final and the initial. And that, in fact, is on the reference table. On the reference table, there's a nice formula sheet. This is literally all of the equations that are provided to you on the reference table. And literally all of them are on like rate of change equations. So so this is the gradient change in field value over distance. So the change in field value, point C is 1,000, point D is at 500. Okay, so 1,000 minus 500 divided by the distance. Now, here's where you may need a ruler to measure, but this is a distance of 2 miles. So a distance of 2 miles is about 2/3 of the way. This actually, I did measure on my paper with a ruler. This distance is exactly 3 inches. So, and this distance is exactly 2 inches. So, I'm sorry. I did, now I actually don't recall the exact. I think this was actually 4 centimeters. Sorry, I think this was actually 4 centimeters. No, I'm sorry, I did write it down. Good. So this is actually on the paper, this is 2 inches. So this is 1 inch on paper, and this is another 1 inch. So this total is exactly 2 inches, and this is 3 inches. Okay. I did measure, I did note it. Thank goodness that I noted it. So divided by the distance, since 2 inches represents 2 miles, 3 inches represents 3 miles. So this is equal to 500 over 3. 100,000 minus 500 is 500 divided by 3, which is approximately 167 feet per mile. So that leaves us with this answer. Okay. If you weren't sure, you could actually visually tell that CD is longer than this 2. So, and 500 divided by 2 is 250. So the answer has to be smaller than 250. That would eliminate choice 3 and choice 4 without any calculation. So, but then the question is it this one or, choice 1 or choice 2? But you do need to know the actual measurement. This one would, choice 1 would require a distance of like 3 2/3 inches. So you do need to actually measure it. But a choice 2 is the one that makes the most sense based on the ruler measure. Letter X is located, for this is number 43, number 43. Letter X is located on which landscape feature? So we see that the river goes down, 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 makes a little loop around X, and then goes into the lake. This loop around X, is it a sandbar, a sand dune, an escarpment, or a floodplain? So let's talk about what these actually are. A sandbar actually divides 2 bodies of water. So a sandbar literally splits 2 bodies of water. There are some places where you could see beaches formed by sandbars. Literally, the sandbar actually splits one side of a body of water and another side of the body of water. And every once in a while, that sandbar gets destroyed and the water flows through. And then the sandbar kind of just reforms, which is a pretty cool, nifty thing. But a sandbar is a solid piece completely dividing 2 bodies of water. A sand dune, this is a mound or ridge or hill of sand. There's nothing to tell us that this is a mound or ridge or hill of sand. And letter X is not, and the point is not completely splitting 2 bodies of water. So it's not choice 1 and choice 2. So choice 3 and choice 4. I mean, if I don't know what an escarpment or a floodplain is, then I might get stuck here. But an escarpment is a steep slope due to a fault or erosion. So this big steep thing is probably an example of an escarpment, but I couldn't know because there's plenty of things that cause steep slopes. But A floodplain, though, is a land which is adjacent to a river. So, well, the entirety of X is adjacent to a river. I mean, so it is a floodplain. And it's not a steep slope. There's no evidence to say that X is a steep slope at all. In fact, it's the entire elevation is contained within two lines. The next line, who knows where that next line is? So we don't know the slope of X at all. So that's why X gets eliminated. Now, number 44, numero 44, the arrows on which map represent the direction of stream flow relative to the pond? Choice 1, 2, 3, or 4. With only looking at choice 1, 2, 3, or 4 without looking at the map above, there's not much that we could do. So in principle, any of these could be it, but then the question is, why doesn't the pond get overfilled? So choice 1 is very unlikely to be it. Choice 3, choice 4 is also very unlikely to be it, because that would mean that choice 1 is a source of water which is somehow replenished, and who knows how. So choice 1 is very unlikely to be it in general. But we do have to look at the map. To really be able to do this problem, we have to look at the map. And we said it again, we've said it before, and this is an important thing, so clearly it really matters. Water runs downhill. Downhill. Water runs downhill. If you remember that as a principle across this entire test, you actually can get a lot of questions right. Right? Just knowing that principle can get you many questions correct. So if we look at this, the water runs downhill. Well, we have a 1,000-foot mark and we have a 500-foot mark. Since we know the water runs downhill, let's use this squiggly thing. The water runs that way and water runs that way because it runs downhill. Water runs downhill. Downhill. I know those that's hard to see, but there's no good color to write on the blue. Water runs downhill, which means on that map, we just drew those arrows this way, leaving choice 3 as the answer, okay? We drew them on that map in that direction. On that note, I deserve a little snack. Again, Fairlife is a great snack to bring with you. If Fairlife wants to sponsor these videos, I will mention it in every single video. That said, número 45 a 47, base your answers to number 45, to question 45 to 47 on the cross sections below and on your knowledge of earth science. The cross sections represent 3 plate boundaries labeled A, B, and C. I do look quickly at them. I see oceanic crust, ocean continental crust with a volcano. I see oceanic crust and an oceanic crust with a volcano. I see continental crust and continental crust and something going on bottom. And that's it. And I analyze it just that far. I just read what they are, let that do what it does in my brain, and then I go on to the problem. And then I go back to them to read them again, if I need to. Número 45, compared to the density and thickness of the continental crust in diagram A, the oceanic crust is less dense and thinner, less dense and thicker, or more dense and thinner, or more dense and thicker. So, well, less dense versus more dense. Do remember, just like, we talked about the oil and water being put in a glass, the oil goes to the top and the water sinks to the bottom because the water is more dense and the oil is less dense. The more dense liquid goes down, the less dense liquid goes up. Now, why am I mentioning here that fact when we're talking about oceanic and continental crust and ocean? The reason is that despite the fact that the land is a solid object, over geological timescales, we're talking about like the age of the Earth. The crust and the mantle behave more like an extremely viscous fluid. They are solid, but over extreme geologic timescales, they do behave a little like liquids. So what that means is that we expect the more dense solids to go down and the less dense solids to go up. So now we're comparing the density and thickness of the continental crust to the oceanic crust, and we want to talk about the oceanic crust. So we want to say what we know about the oceanic crust. Okay? So make sure we answer the question about the oceanic crust. In diagram A, notice that the oceanic crust is going down like the denser stuff does, which means that the oceanic crust is denser. Denser materials sink, less dense materials float. So the oceanic crust is more dense, not less dense, not less dense. So we have eliminated two choices and we have a passing problem. Remember, a passing problem is one that leads you towards a passing grade. When you eliminate two choices, it might feel like that's not worth your time, but it is a passing problem. No matter where you are, trying to get your 65, trying to get your 80, trying to get your 90, trying to get your 100. Getting up to a passing problem is super beneficial. If you struggle with these problems, well, getting a passing problem, you might be 90% of the way because you might be able to eliminate one of the other two choices. Whereas if you struggle and you're really aiming for that 65, you shouldn't aim for the 65. You should aim for as high as possible. Don't aim for a 65 because that makes you make decisions, gambling-ish decisions. You want to aim for as high as possible, which means you want to maximize your grade on every single question. Now we have to look at thinner versus thicker. Actually, we could just look at the diagram. Which one's thicker? That or that? That or that? Which one's thicker? The bottom one's thinner. The top one's thicker. The oceanic crust, which is the bottom one, is definitely thinner. Thinner, not thicker. So the answer is choice 3. And in this case now, which diagram is best represent? No, which diagram best represents the relative motion of oceanic crust at plate boundary B? Let's go to plate boundary B, the oceanic crust. So we have two pieces of crust moving, and one of them is creating a volcano, and the other one seems to be under the other one. So which one of these is happening? So let's look. These are all matching the shape of B. The question is the arrows, though. So we have to know which of these are actually occurring. So an ocean trench happens in an ocean. And think about the Mariana Trench, Challenger Deep. When you take ocean crust, let's pretend that these are ocean crusts. My fists are ocean crusts. And these two, one of these two choices, they're actually moving apart in choice 2. If they're moving apart, look what happens to my fists. Look what happens in between my fists if you're moving them apart. Look at that valley created. And no matter what, you're moving them apart, you're creating this valley. The Mariana Trench, there we go. That's what forms it. Crusts moving apart. So this is in an ocean where plates are spreading. Plates, that's a P, are separating. And you get something like this. You get a valley. Not really, I mean, you might get volcanic, I think you do get volcanic, you do get volcanic activity, but you get a valley. You get a valley. This forms a valley. So that's not it. A rift valley. Wait, I'm actually doing 47 at the same time, so I apologize about. But it's actually worth talking about it. Let me just see. Give me a second. Yes. So sorry, I have to go back to 46. Again, I'm not fixing any errors. But that happens. An ocean trench. This would form an ocean trench. So that does not happen here. Okay, so there we go. So what about this one? if these move in the same direction, then generally speaking, not much is happening because they're literally moving like this. Not much is happening. So plates don't I mean, they can move a little bit relative to each other, but then you have to look at their movement relative to the rest of the Earth. But relative to each other, they can't do this because then they're not moving relative to each other at all. They could either move apart. This is a three-dimensional thing, so they could either move apart or they could move closer to each other, or they could move horizontally relative to each other, so they could grind. Okay? So, and they're not giving us the option of them grinding against each other. So it's either they're splitting apart or they're coming together, so that eliminates choice 4, where they're moving in the same direction, and then it eliminates choice 1, where they're moving in the same direction. So actually, now that actually told us which one it actually is. So again, this one, the reason it's not this one is I explained it accidentally for choice 7 because it creates a valley, not this volcano. But it's important to know that what is happening here is that one of the plates actually subducts below the other plate. And as that's happening, a lot of heat is generated, which makes these volcanoes occur. So it is choice 3. Now I explained part of number 47, número 47, which geologic surface features created at plate boundary C. This is a nice mountain here, not a valley. So we already have explained why the ocean trench is not the example, not the truth. Now our Rift Valley, same deal. A volcanic mountain. So in number 1 and choice diagram A and B, we see volcanoes. Diagram C, we see no volcanoes. So there is no volcano shown. So that's why it's not the answer. Now, however, a folded mountain, you actually kind of see all the foldings that occur in diagram C. So a folded mountain is it. Accidentally did part number 46 and 47 kind of together, but that's super okay. All right, 48 to 50. Base your answers to question 48 to 50 on the passage and photograph below and on your knowledge of earth science. The photograph shows a typical Petoskey stone, Petoskey stones, which are really cool. I think they're pretty. Petoskey stones are famous rock specimens found on the beach all around Lake Michigan, but especially on the beaches near the city of Petoskey, Michigan. Lake Michigan, that's the United States. Around Petoskey, Michigan, the stones are actually well-eroded pieces of coral reefs, that's cool, that were alive between 375 and 400 million years ago. Okay. At the time, the coral animals, yes, corals are animals, were living and forming reefs. The area was underwater, and the coral, along with many other reef animals, thrived. Eventually, the ocean disappeared and the fossil reefs were uncovered. Advancing and retreating glaciers broke pieces off the fossil reefs, smoothed their edges, and distributed them throughout the area. Lake Michigan, along with the other Great Lakes, formed at the end of the Ice Age. Today, lake waves continue to distribute a seemingly endless supply of Petoskey stones with their unique coral fossils to the beach and Lake Michigan. All right. So the coral eventually became Petoskey stones were alive during which geologic time period? Is number 48. There we go. There's number 48. Now they just said 375 to 400 million years ago. Okay. So if we go to page 8, 375 to 400 million years ago. That's between this and this. So there's no guessing and checking. Between 416 to 359, which includes the time from 375 to 400 million years ago. That is the Devonian. Page 8. There is no guessing and checking there. Okay. So the next one, which number 49, number 49, which New York State index fossil is in the same group of organisms as Petoskey stone coral? The same group of organisms as the Petoskey stone coral. So the same group of organisms, this is where we go to page 9. And if you see this giant column, coral goes all the way down to here, all the way up. And if you see which group, so in the top, the label does say over here, the centers of each lettered circle indicates the approximate time of existence. I know those letters are small. Existence of a specific index fossil, e.g. fossil A, lived at the end of the early Cambrian. So here we have the corals, which includes group T, U, and V. So the answers are fossils T, U, and V. And now what are T, U, and V? Actually, those are also on the reference table. You keep scrolling to the bottom. T, U, and V. Oops. From this, right? This is why we're going for T, U, and V. Okay, so T, U, and V are any of these three that appear in the choices. Here's the lichinaria. Perfect. Does the cystophyllum occur here? That's not there. And does the pleurodictium appear there? No. So the only one that appears there is just choice 1. None of these are included in the T, U, or V. That's why those are wrong. Literally a reference table question. So now I didn't know how to do this question initially, so I didn't realize that that's what it was talking about. So after reviewing it for a while, including the review materials that are provided to teachers and accessible to students, I got that answer. I will note this again. If you look at the NYSED website, the Earth Science website, one of these is the scoring key and the rating guide. The scoring key and the rating guide. And one of them says in big, is that it? Sorry about that scrolling. That's not it. In big fat letters for teachers only, but it's publicly available. And you should feel extremely welcome to look at it. Do understand this for teachers only doesn't mean that you're cheating by looking at this. It actually, a lot of students are like, oh, I'm cheating if I'm looking at this. No, it's actually materials that are available to you eventually. It's just that it's not available to you when they're grading. So teachers have this available to them after the Regents is taken, but it's in fat letters for teachers only, so that teachers know not to give this to students. Back in the day when I was younger, these things were literally delivered to schools. The Regents are still delivered to schools, but these documents were also delivered to schools, and now these documents, the teachers only documents, are online. They're not delivered to the school, so it's impossible to mix those up now. But that's why they're there. Okay. Anyway, número 50, number 50, the Petoskey stones shown in the photograph is classified as a sand, pebble, cobble, or boulder. Great question. I feel like sand is not the answer, although what is a boulder? What is a cobble? What is a pebble? Turns out that this is a reference table question. And we go to page 6. And if we go to page 6, we look at rock sizes. I know boulders tend to be quite big, but how big do they have to be before they're boulders? I mean, in principle, it's a definitional statement, right? So how do I know? If I go to this picture, sand, pebble, cobble, or boulder, I have to go to the diagram and it says actual size. So I actually see the 0 centimeter mark to the 6 centimeter mark. This is a 6 centimeter object. So I go to this diagram, and I see stream velocity and particle diameter. Particle diameter goes from 0.0001 centimeters to 100 centimeters, and the 6 centimeter mark is between 1.0 and 10.0. 1, 2, 3, 4, 5, 6. I know this weird line is these weird markings are in skipping for some reason, but that's called a logarithmic graph. And even if it's confusing to us, we actually just see the labels. We're between 1.0 and 10.0, and they do label the 6.4, which shows what that's a cobble. We are below 6.4 because we're at 6.0, so we are in the pebble range. So that's why this thing is a pebble. I wanted to cross out sand so badly, but I didn't know, because what's a sand? I didn't know. And boulders tend to be bigger, so I'm like, I felt like that should just be crossed out. But then a boulder turns out to be starting at 25.6 centimeters. And I know that a foot is 30 centimeters. So if I have a rock that big, that's already a boulder. It's slightly less than a foot. But this one is like that big, 6 centimeters. So it's considered to be a pebble. All right. Part B2, kind of the same as B1. So I really don't separate the differences between B1 and B2. The differences in structure don't matter. But B2 is again multi-part questions that we do on the using the reference table. Except that starting at this point, we're going to start filling the blank questions. So every single question from now on is a fill in the blank question. Okay. Let me get my answer key out just so I know that I'm not accidentally skipping anything. And I go to 51 through 54. Base your answers on to questions 51 through 54 on the weather map in your answer booklet, which is right here. So if you're wondering, and on your knowledge of Earth science. The weather map shows air pressure in millibars at locations on the on and around the Florida Peninsula during Hurricane Wilma. 5 hours isobars are shown. Isobars, same bar pressure. Okay. On the map in your answer booklet, draw the 1000 millibar and the 1004 millibar isobar. Extend the isobars to the edge of the map. So we have to connect the dots. This is a connecting the dots. I see 1000 here, and I see 1000 over here. So there's 2 points that I have to connect. How do I possibly connect those with lines? I have to connect, or with curves. I don't have to draw perfectly straight lines, and in fact, isobars tend to not be perfectly straight. The only conditions that they're grading against is that you connect those and you make sure you stay between numbers that where it makes sense. For example, between the 1003 and the 997 should be 1000 because pressure changes continuously. Pressure changes continuously. So if you do this above the 1003, that means that it's not between the 997 and the 1003, so that's got to be wrong. And if you go this way, that's also got to be wrong because that's between the 997 and 996. So I go this way. I go to the edge, make sure to go to the edge, and I keep going this way between the 997 and 1003. I keep going this way. Now I have 1001 and 999 and 1006. I got to be between the 1001 and 999. So I keep going. And I keep going. The 1005 is here, so I got to stay to the right of 1005. And now I have 1004, 1000, and 997. I have a nice dot to connect to. And now I have 998, 997, and 1002. I got to go between the 1002 and the 998. And I keep going. Now, if your line hooked this way, doesn't matter. If this line hooked this way, or that way, or that way, or this way, that doesn't matter either. And in principle, those are possibilities. So it's not actually incorrect. As long as your curve connects the dots 1000, and you got to go perfectly through those dots. If you miss the dots, point off, because it's just 1 point. Then you lose points. Okay. The second one, the 1004, I see a dot 1004, and I see another dot 1004. I got to connect those dots between, I got to say again, between the correct numbers. So 1007, 1005, I got to stay to the right of the 1005 and between the 1005 and the red 1000. Then I keep going to the 1004. Then when I keep going, I got the 1000 and 1006. I got to go between those. I see the 1002. I got to go below the 1002. And there I am. Okay. But I didn't finish the bar. So I got to keep going up. I got to stay to the left, to the right of the 1008, to the left of the 1000, and to the right of the 1006. I see 1003. I got to stay to the left of that because this is bigger. Between the 1003 and the 1006. So that makes sense. There we go. There's my isobar. I didn't even draw it exactly this way when I did it the first time. My curviness was a little bit different. The only conditions is that you got to connect the dots correctly. That's it. And you got to connect the dots correctly and stay between the correct, the lesser and the greater measurements. That's a full credit answer right there. Número 52, number 52. Convert the air pressure of the lowest value isobar shown on the map from millibars to inches of mercury. Okay, so here is the lowest air pressure, lowest value isobar shown from millibars to inches of mercury. Here's the lowest value. Let's highlight that in what color? Magenta. That's a little bit hard for me as a colorblind person, so it's probably hard for you. Let's go for a cyan. Here's the 984. That's the lowest one. And how do I convert this? It's actually a reference table question. Page 13. Oh, too far. Page 13. I'm going to, so 984. 984. Right there. I'm going to screenshot that. I wish this thing would not show up there. There we go. And I need to convert that. And let me just make sure I mark that. Millibars to inches of mercury. Okay, so I'm doing this right. And I see that's 29.00 to 29.10. This is 29.05 is that line. So 29.05 and that line is 29.06, so maybe 29.05, 0.055 or something like that is an answer. And so that is, I'm going to give 29.055 inches of mercury. This part is already contained in the answer sheet. So if you just gave that number, and they did accept anything between 29.05 and 29.06. So you don't have to be so obsessively accurate as I was, although being obsessively accurate does help you because you're less likely to be wrong. Okay. The next one, identify the weather instrument used to measure the air pressure. I mean, the fact that it says bar all over the place is a big hint. And in fact, the reference table on page 13 has a hint right here of the barometric pressure. Barometric pressure. And the object that measures the pressure is called a barometer. Or if you're from another country, maybe you might have called it a barograph, but barometer. Or maybe because of this table, maybe you used it as a graph, okay? But barometer is the object. Write the two-letter weather map symbol for the type of air mass in which this hurricane formed. The two-letter weather map symbol. So that's again on page 13. So hurricanes, this does require a little bit of knowledge of of Earth Science. Okay. Here is our diagram. Continental Arctic is farther north. Continental Polar, further north. Continental Tropical, further south. Maritime Tropical, further south. And Maritime Polar, further north. So it's either tropical, it's either a sea, it's tropical is the one that makes more sense. It is important to know the path that hurricanes take. Hurricanes literally start from literal Africa. Literal wind blows with dust from Africa, goes over the ocean. But it doesn't start as a hurricane in Africa. It starts just as a wind gust with dust. And that wind gust goes over the ocean, at which point it's a maritime tropical air mass. And that maritime tropical air mass collects a bunch of water and starts spinning, and the dust collects water and becomes a hurricane. So that maritime tropical is the answer to this question. And so the two-letter weather map symbol is MT. Okay. The hint was, again, hurricane. You do need to know that the hurricane literally starts from wind coming from Africa with dust going over the ocean, collecting air, collecting water, and becoming this major storm and starting to spin also due to the Coriolis effect. Okay. And then eventually it is a hurricane, hits Florida, sometimes goes up north and curves back around, sometimes hits other land like New York, sometimes occasionally goes over the continental part of the United States. All right, base your answers. Actually, there's a hurricane going through Florida, gonna hit Florida right now, so which happens somewhat frequently during the school year, during the summer. Not usually during the school year, although it has happened. But let's see, number 55 through 57. Base your answer to question 55 through 57 on the passage in the data table below and on your knowledge of Earth science. The data table shows garnet coefficients and rock formation temperatures. Garnet coefficients and rock formation temperatures. Okay, I don't know what those are in principle, and you probably don't know either in principle. I did know what they were from previous, Earth Science Regents, but this is going to tell us how they're used. So even if you don't know how to use it, fake student me might not know how to use it, but I get to be told how they're used. So let's see what they say. Using garnet as a geothermometer. A geothermometer mineral is a mineral with slight differences in composition that can be used to estimate the temperature at which some types of metamorphic rock form. Garnet is a geothermometer mineral because there are several kinds of garnet that contain different amounts of iron and magnesium. The garnet coefficient indicates the ratio of iron to magnesium found in the garnet. When the garnet coefficient is high, there is a greater percentage of iron compared to magnesium. The garnet coefficient is an indicator of the temperature at which the metamorphic rock formed. Okay, that was a lot of information. But then I look at the table and I briefly read the table and then I go back to the table as needed. So the garnet coefficient and the rock formation temperature. I see garnet coefficient. I see it generally speaking going up from 1.22 to 1.70. And I see the temperature at which rock formed going down from 720 down to about 570. That's information. Here's a garnet, pretty cool rock. Determine the rock formation temperature for a rock sample with a garnet coefficient of 1.55. So that table, I go back to the table and I look for 1.55, which is definitely not there. Okay, but if I look for a garnet coefficient of 1.55, it's definitely between 1.47 and 1.63. So 1.55 is right there. And I go across. And I see it's got to be between 640 and 590. They will allow basically any temperature between these two. But since 1.55 is exactly in the middle of 1.47 and 1.63, might as well choose a number that is exactly in the middle of 590 and 640. How about 615? 615. So I'm going to choose 615, which is exactly the number in the middle of 590 and 640. But they would have actually accepted kind of a range of temperatures as long as they're strictly between 590 and 640. 615 is a good temperature uh, to choose. If you decided to use like trend lines or anything like that, you could have done that, but that would be that, and that would give you maybe a slightly different answer. But I like the 615 answer. 610 or 620 would have also been full credit. Número 55, no, I'm sorry, número 56, number 56, describe the rock formation temperatures that are indicated when higher Garnet coefficients are found. So higher. And we see lower temps. So the question is not asking you what the temperatures are. So they're asking you what the trend is. So this goes higher, and this goes lower. So you could say something like inverse relation. So inverse relation would have been expected. Negative relation would have been accepted. Any of those words would have been accepted. Okay. Número 57, number 57. Identify one foliated metamorphic rock for which the Garnet coefficient might be used to determine the temperature at which the rock formed. Foliated metamorphic rock. If you could do this without using the reference table, good for you. Again, I immediately go to the reference table, where the reference table actually starts talking about the the rocks, right? I see non-foliated and I see foliated, right? And then what else did it say? Foliated metamorphic rock. Type of metamorphism. Okay. So if I see low grade metamorphism of shale, and this one, foliation surfaces shiny from microscopic microcrystals, or platy microcrystals visible from metamorphism of clay or feldspar. And well, there's a lot here, right? But how can I decide between these? Uh, it's tough if I actually go to the composition column. There we go. So let's actually take a screenshot of this. Foliated metamorphic. So I used foliated metamorphic to determine the correct column to look at. And if I look at, this is all Garnet coefficient. So if I look at garnets, there is garnet here. And it goes all the way across. All the way across. And so actually any of these would have been a valid answer. So they said to identify one. If I said garnet, no, sorry, garnet is not. If I said the rock name, they identify the rock name. If I said phyllite, remember just one. So that would have been a correct answer. If I said schist, that would have been correct. And if I said gneiss, that would have been correct. Any one of those three answers would have been correct. Notice again, I mean, this is the real important part, the garnet. Okay. So that's what eliminates slate. That's what eliminates slate. Okay. Any one of these would have been correct. All right, let's move on to 58 through 59. Base your answers to question 58 and 59 on the map and the graph below and on your knowledge of Earth science. The map of Australia shows the locations of 3 cities. Let me shorten this a little bit. Okay. Brisbane, Melbourne, and Wagga Wagga. Wagga Wagga. So the graph shows, let me just turn my page. I saw that the word Wagga Wagga means dance and celebration. Okay. They used to have some names that people just kind of gave to it, but it was kind of almost like a Western name, Wagga Wagga, Western translation. If you go back to the Aboriginal translation, Wagga Wagga represents dance and celebration. Okay, so anyway, 3 cities, Brisbane, Melbourne, and Wagga Wagga. The graph shows the average monthly temperatures in Wagga Wagga and Melbourne in degrees Celsius. So here's Brisbane, Wagga Wagga, and Melbourne in this graph, and here are the temperatures. I see the graph of Wagga Wagga going up and then back down and then back up again, and the temperature of Melbourne going up and then back down and then back up again, and they kind of cross. So there's a bigger variation in the Wagga Wagga temperature and a lesser variation in the Melbourne temperature. Okay, and I see the months. So JFMAM, that's January, February, March, April, May, June, July, August, September, October, November, December. So this is from the beginning of the year to the end of the year. Okay. Compared to the average monthly temperature curve for Melbourne, describe how the average monthly temperature, air temperature curve is different for the city of New York State. New York State. Notice that this one in Australia, in Melbourne, starts high at 20 degrees, dips down to 10 degrees for July and August, and then goes back up to 20-ish degrees in December. So in our winter, they have the hotter temperatures. That's their summer, which is not surprising because in the southern hemisphere, northern winter and southern summer occur at the same time. Southern hemisphere summer and northern hemisphere summer and southern hemisphere winter happen at the same time. So what you could say, since we live in New York in the northern hemisphere and we get the colder days in January and December and the hotter days in July and June, you could say that these are the curves are inverted. Okay. You could also even be more wordy and say that when the temperature at Melbourne increases, the temperature at New York decreases, and vice versa. When the temperature of Melbourne decreases, the temperature in New York increases. You could use all those words, or you could just say something as simple as the curves are inverted. The curve in New York, well, it really depends on where in New York it is, but it goes like this. And 20, it goes even higher than that. So it goes, okay. This is NY. Okay, so now in your answer, you didn't have to draw that, but I drew it just for our own edification. Número 59, number 59, in your answer booklet. Oh, I didn't even realize I put this on here. Okay. So in your answer booklet for number 59, número 59, in your answer booklet, circle warm to cool to indicate warm or cool to indicate the relative temperatures of ocean currents that flow off of the coast of Brisbane and state the name of this current. Again, I don't know if you'd be able to do it. Brisbane. Warm or cool and the name of the current. That's literally the reference table. So if we go to page 1. No, not page 1. Page 4. So yeah, I did write page 4. Okay. Page 4 off of Brisbane. Now going back to going to this map and then making sure that we're at the correct side. Brisbane is on the east side of Australia. So if we look on the east side of Australia right over here, well, it's these dark arrow currents. So now we have to look at the key. The key dark arrow currents are warm currents. Okay, warm currents. So that's definitely, we should circle warm. But the name of the currents are the East Australia current. So East Australia current. Can I put a just C dot? Well, that's what they gave, C dot. So yes. All right, 60 to 62. Base your answers to questions 60 to 62 on the cross section below and your knowledge of Earth science. Let me minimize this a little bit. The cross sections represent changes in the land at Montauk Lighthouse, Long Island, between 1838 and 1988. The Montauk Lighthouse, built on unconsolidated sediments, is located on the easternmost tip of Long Island. The distance from the center of the lighthouse to the edge of the escarpment is indicated in the cross section. All right, so we look at this 220 feet to 100 feet, 1938 to 1998, I'm sorry, 1838 to 1988, that's 150 years, and we see the ocean. Identify one agent of erosion that removed the sediment and changed the position of the escarpment between 1838 and 1988. They don't expect you to be an engineer. They just expect you to give just one of the many things that you could think of that caused that erosion. The one that I gave for my answer is ocean currents. As the ocean currents move by that area, they take away rocks and pebbles and things like that. So that takes away, that can cause landslides, small landslides, and things like that. But you could have also said erosion. You could have said rain. Oh, so agent of erosion. You couldn't have said erosion. One agent of erosion. You could have said rainfall. You could have said snowfall. You could have said freezing and thawing of water, which does happen, of course, in New York. We know we get ice in New York. Lots of different causes here. Number 61, número 61, calculate the rate of erosion in feet per year between the lighthouse and the edge of the escarpment that occurred between 1838 and 1988. Express your answer to the nearest tenth. Okay, so we have a difference of 220 feet to 100 feet. And that is a formula that is on the formula sheet. That's one of the reasons why we are required to have a calculator accessible. Okay, so equation. So let's put that in here. So gradient or rate of change, which is change in value over change in time. Here's the equation that we need here. So let's actually do that equation. Change in value. The distance went from 220 feet down to 100 feet. Which is equal to 120 divided by a change in time, which is 1988, minus the starting time, 1838, which is equal to 150. So the answer is 120 over 150, and we put that in our calculator. 120 over 150 equals 0.8. 0.8 feet per. And the feet per year is already in the thing, so you could actually just give the 0.8. Okay? It's in the answer sheet. Número 62, number 62, describe one action that could be taken to slow down or prevent the future erosion of the land between the escarpment and the ocean. This one, again, this is another one. They don't expect you to be an engineer. They don't. You're a high school student. So any solution that you can think of that is just even remotely plausible is good. If you said something as silly as like magical fairy dust holding the thing together, then you would not get credit for that one. However, if you actually turned the magical fairy dust answer into a more realistic answer, like literally anything that's more realistic, like placing a tarp that prevents the rocks from sliding down, that's probably not something that is the best solution, but it is an allowable solution because literally you're not expected to be an engineer. You're literally just expected to be a high school student that can create plausible solutions. Now, the one that I put in, I put placing large, replaceable metal spikes in the ground to prevent rockfalls. But literally anything. I mean, that's what I put in. I don't even think that that's necessarily the best solution. You could put, excuse me, large replaceable wooden spikes. The wooden spikes would get dissolved by the ocean, sure, and eaten up by different things. But we know that there's wooden barges out there, so they get eaten up, they get dissolved. You replace them more often. But wood grows on trees. Wood is literally made of trees, so you could replace them a lot more cheaply than like metal, which is a non-renewable resource, or putting a tarp, or you could even have said things like putting plastic a plastic layer to prevent the ocean from crashing into the rocks. Um, any not unfathomable solution is valid for that question. So I just want to give you, I want you to understand, this is not like 62 is not a question that you would ever want to skip. Um, I should mention also, notice that all of these questions have been non-multiple choice. Can you pass the test by focusing on the multiple choice? Just like I told students who take the math, that focusing on the multiple choice by showing work is the best strategy, because then by showing work, then you should do the same showing work on the part twos, threes, and fours. And if you're not showing work, then you're not really focusing on the part ones. Except for this one, you need so many points that just focusing on the multiple choice is very unlikely to just give you the passing grade, because you literally, unlike the math, if you get about half plus one question on the multiple choice, you pass. But you should show all work anyway so that you can get like an 80 instead of a 65. You literally need to get 80% of the multiple choice to pass this test. That's too much. So you need to focus on every single question on this Regents to pass this test. You really do. So number 63 to 65. Base your answers to question 63 to 65 on the data table below and on your knowledge of Earth science. The data table shows the sun's altitude and the shadow length measured from the base of a 5-meter high pole on June 22nd in Rochester, New York. During the daylight saving time, clocks are set 1 hour ahead so that solar noon occurs at approximately 1 p.m. Okay. Okay. On the graph in your answer booklet, construct a line graph by plotting the altitude of the sun for each time of day shown in the data table. Collect all 10 plots with a line. The shadow length data have already been plotted using the scale on the right. Okay, so shadow length data, and now the altitude of the sun with the data on the numbers on the right. So we have to literally go for the altitude data. One place where a lot of students struggle on this one and get a question wrong is that they look at the wrong numbers. Okay, so 9 a.m., 35, 35. Oop, see, already points off. 9 a.m., 35. Okay, 10 a.m., 46, 46 and then 56 at 11 a.m., 10 a.m., 46, 11 a.m., 56, oops, 46 and 56. Okay, so now you keep going up and you literally are looking across, right? You're looking across. the way you're literally looking across, looking across, looking across. That's how you're literally graphing this, okay? So now I'm going to graph the rest of these from my paper. 12 a.m., 12 p.m. rather. 1 p.m. I got to check if this is 69 or 70. 1 p.m., 70. And 2 p.m., 68, I believe. I do have to check the numbers. 2 p.m. Was 68. 3 p.m. was 60. 4 p.m. was 50. 5 p.m. was 40. And 6 p.m. was 29. Okay. And then connect these. You do not have to connect these with a, well, they connected these with a ruler below. So they did say to connect it with straight lines. So you got to pull out your straight edge. Okay. My software makes lines straight. So I am using my software to do it. But I am using straight lines. So I'm using my straight edge, right? That one did not come out straight for some reason. Let's try it again. Okay. There you go. So they did use straight lines on their first graph, so I use straight lines on my graph. Okay, and that's a full credit graph. Now the 64, 64. Let's scroll down to 64. Based on the data table, describe the relationship between the altitude of the sun and the length of the shadow. You notice that the sun height goes up, the length of the shadow goes down. So this is an inverse relationship. If you just said inverse relationship, you could have said as the altitude as the sun grows, the shadow length decreases. Uh, you could have said as the altitude of the sun decreases, the shadow length increases. You could say that a relationship is an inverse relationship. You could say it's a negative relationship. All of those would have been valid answers. Number 65, número 65, based on the graph, determine the shadow length of the pole in meters at 4:30 p.m. So 4:30 p.m. Go to 4:30 p.m. and right there. And so the shadow length is on the right side. So that's 5. 5 meters. Okay. This is what I got stuck on. So let's talk about it. Now I will say about this before I even read number 60, 67. Notice, by the way, that this section is nearly identical to the previous one. It's literally again a part. It's like part C is literally again using your reference table and using information. But I sometimes like um I guess I had this weird ability to think in geologic timescales, like millions and billions of years, because all of the time lengths are more like relative as opposed to being just big. So I could think of something that occurs in 4.5 billion years just as easily as I could think of something that occurs in 4.5 minutes. Why am I mentioning that? Because layers, you could think about layers forming the same way you would build a cake. Uh, and so you could think about how a cake would be built if you did this, if you looked at the details here. And so instead of having to think of geologic timescales, we could think of kind of minute by minute timescales. How would you build a cake that looked exactly like this one? All right. So that's my advice. Okay. So base your answers to questions 66 to 67 on the cross section below and on your knowledge of Earth science. Okay. Letters G and H identify some rock layers. the wavy line WX indicates an unconformity. And line YZ indicates a fault. Index fossils are represented in some rock layers. Rock layers have not been overturned. Okay, so let's give some definitions just so you have them. What is an unconformity? So an unconformity is a buried, erosional, or non-depositional surface separating two rock layers. Or rocks of different ages. So unconformity is a buried, erosional, or non-depositional surface separating two rock masses or rocks of different ages. So how could that possibly happen? Somehow the rock below have one age, the rock above have a different age, but there's no continuity between the rocks ages. When rocks are deposited, yes, the rocks of a certain layer have similar ages, but the bottom layers and the top layer of the same the bottom part and the top part of the same layer have different ages. So there is a smooth transition in age from one layer to another, even if the layers are very different. But an unconformity is when there's an actual break in the timeline, almost like part of the timeline is just missing. Okay? So the next question is identify the most likely geologic time period during which unconformity WX was forming. So I initially struggled with this question because I was looking at the rock type but then I'm like, rock types match in some of the layers, and then I realized that I should actually be looking at the fossils, okay, to identify the most likely time periods. So if I look at the fossils, going back to my formula sheet, my reference table. Now, for some reason, I say look at page 3, but that's actually not correct. If I look at the fossils, so you see that there's these fossils over here on bottom of page 8 and the bottom of page 9. And I know that there's a break in page 8 and page 9, but remember that on the reference table, page 8 and page 9 are literally next to each other, which is the way it should be. So you could look at these at the same time on the reference table, and you could see the fossils below. So you could actually see where these fossils occur. So you have to look at the pictures of the fossils and see where they are, okay? So I see one fossil at V, okay? I'm gonna put a V here. Now, I don't want to confuse things with these letters here. And I see another fossil here. So let's see if I could look for this fossil here. I see fossil D, okay? And then I see this fossil here. I see a fossil A, okay? And then I look at when these fossils were actually formed. And fossil A, I have to go back to this one again. So these are not next to each other, so I know that it's not the best situation. Maybe next time I do this, I'll make one screenshot of slide of 8 and 9 so that they are actually next to each other on a separate PDF. Okay, so A is this last bottom bar, and the last bottom bar is the Cambrian. H is right here, the third to last bar, the third to last row. The third to last row is the Silurian. And then V was formed in the fourth to last bar, which is the Devonian. Sure, I got that right. Give me 1 second. V, the fourth to last bar. Oh, that's why I got confused, because this D was the second to last bar, and H and V was the fourth to last bar. So D was the Ordovician. And then the fourth to last bar was the Devonian. So if these layers were formed in that order, so then the question is, when was this break formed? And there are arguments for 3 different answers. There are valid arguments for 3 different answers. You don't know how long it took to make layer marked with G. So the layer marked with G had to be between the Ordovician and the Devonian. So I think the best answer that I would give is the Silurian, but also the Devonian and Ordovician would have been valid. So the answer that I gave is the Silurian, but it would have also been valid to say the Devonian or the Ordovician. And the answer that I actually gave in my sheet is this one. But all of these are valid answers. And there are reasons for which we don't know exactly which one of these it was. But again, the one that I gave, they said which most likely geologic time period. If you gave the Silurian, Devonian, or Ordovician, you would have been correct. And I gave the Silurian. So notice that it's not the rock types that told us the answer. It's actually the fossils that told us the right answers. I think it's a fairly interesting question that way. And I actually should say that K does appear. I guess initially when I was looking at it, I didn't even realize necessarily that K was there. Because tell you, and I'm being honest right now, to tell you the truth, I was looking for K, didn't see K. I guess maybe because they rotated it by 45 degrees, somehow I didn't see it. But K is also in the Silurian. So that's actually, I'm sorry, the Ordovician. So that actually doesn't change the answer. So either way, Ordovician to Silurian to Devonian, or Ordovician to another Ordovician break to the Devonian. There's no way, since there's erosion that happened, the erosion could have been happening in any of those 3 time periods. Okay. That said, number 67, número 67, in your answer booklet, circle the term that best describes the relative age of fault YZ compared to layers G and H, and describe the evidence that infers this relative age. Again, we might have trouble thinking in like geologic age, things that happen over millions to billions of years. But if we imagine it building a cake, we build cake. Somehow there's a slice here, and then cake. The question is fault YZ compared to layers G and H. Can you form this fault which splits right through layers G and H before you form layers G and H when you're building a cake. You have to form G and H first, cut the cake, somehow move a piece of the cake up, and then so you make the fault after you make layer G and H. And then if you wanted to argue, then you could keep going, make Y, X, and then put the layers on top of that. But either way, G and H have to be formed first, and then Y, Z has to be formed afterwards. So the question was the relative age of fault YZ. YZ is the age that we're talking about, has to be younger than layers G and H. So we circle younger. Okay. And now what is the evidence? So again, the evidence is that the fault cuts through G and H. Oops. So G and H had to be formed first, and then that fault occurs. So if I had to make an age order, G and H are formed, then the fault happens. Then since the WX discontinuity cuts through the fault, WX is younger than fault YZ, and then the rocks on top are likely younger. And in fact, the fossils tell me that the rocks on top are younger. Okay. So number 68 through 71. I like this one because it talks about stars locations. Base your answers of question 68 to 71 on the data table and passages below, and on your knowledge of Earth science. The data table shows the location and characteristics of 7 stars, numbered 1 through 7, found in the constellation Cygnus. This is a big table. You're not expected to input all of this information into your brain so instantly. That's not a thing. Not even a thing for me. Yes, there are some people who could look at this table and memorize it instantly. Those are very special people. For me, I do look at the chart before keeping going, but I just let the data do what it does when I look at it. Real quick, location and characteristics of 7 stars in Cygnus, star number 1 through 7. Here's the star names, cool. Celestial longitudes with some numbers, celestial latitude with some numbers, their temperatures, and their luminosity, cool, with some numbers. The mystery of Tabby's star. Located in the constellation of Cygnus, there is a mysterious star named Tabby's star that has a constant luminosity, but has a brightness that appears to change in a cyclic manner. A team of astronomers has developed a plausible explanation for this change. A dust cloud with a variable thickness has an approximate 700-day period of revolution around Tabby's star. Why dust? The astronomers observed that a portion of the electromagnetic spectrum having wavelengths just shorter than visible light is blocked out, causing a decrease in the apparent brightness. While astronomers don't know the origin of the dust cloud and Tabby's star, around Tabby's star, dust unevenly spaced in this orbit around the star would explain the cyclic dimming of Tabby's star. Now, problem 68. On the grid in your answer booklet, plot the position of the stars 1 through 6. Record the star number of each star besides the plot. In order to create the correct shape of Cygnus, connect the plots with 2 lines. The first line connects plots numbered 1, 2, 5, 6. The second line connects the plots numbered 4, 2, 3. This position of Tabby star number 7 has been indicated with a cross hash circle. So, and this is what Cygnus looks like in the sky. Not with that bright bird, of course, because that's something that we add to it after the fact. But let's look. So we have to go across that said celestial longitude and celestial latitude. So we literally have to go across, and these are the numbers that we're plotting. And then these are the numbers that we're plotting. Okay, so let's go for the first one, 20.7 and 45. Now, this one might be a little tricky for a lot of students because we see that the numbers on bottom decrease from right to left, so they increase from left to right. So 20.7 is actually here, and then 45 is here. So we're going to put a circle with a cross hash, and then I'll put the rest of these here. Same deal. 20 0.3 and 40. Let's move that over a little bit to make it better. 20.3 and 40. The mistake that a lot of students make is they put it to the wrong side because the bottom axis is decreasing from left to right, so it's increasing from right to left, which is a little tricky thing. 3, 19.8 and 45. Let me just confirm that on the table. 19.8 and 45, good. Just making sure I was doing it right. 4, 20.8 and 34. 20.8 and 34. 5, 20.0 and 35. And 7, no, 6. Make sure I got this right because I just labeled that incorrectly. 19.5 and 28. 19.5 and 28. That was 6, and you do have to number them as they said. So this is 5. This is 4. This was 2. This was 3. This was 1. And they, oops, 1. And they said to label these with a line. Why is it not erasing? There we go. Okay, 1. And they did say to connect these with a single line. So I'll connect it with a single line, sure. And then they said connect the other ones with a single line. So I'll do that. Since they said connect them with a single line, you're not incorrect to label them with a single line. Notice that this diagram has them connected by like multiple straight lines, but they just said to do it with 2 lines. So you are not incorrect for labeling them with 2 lines. Let's actually look at how they gave the answer. This is for problem 68. So they actually gave it with jagged lines. So, but they did say with 2 lines, so they would have accepted. Allow credit if the lines do not pass through student plots but are still within or touching the circles, which this one is. It is recommended that an overlay of the same scale as the student answer sheet be used to ensure reliability of the rating. But I mean, and some teachers do that. For teachers, I mean, this is earth science, not math. So some teachers might struggle with the overlaying. But this is a perfectly valid answer. They did say 2 lines, so this answer is valid. If you had done it with straight lines, individual straight lines, clearly that would have also been valid. So if you had done it with straight line there, straight line there, a straight line there, straight line there, and a straight line there, either one of these answers would have been valid, the blue lines or the red lines. Okay. Now identify the planet. Number 69. Identify the planet in our solar system that has the same period of revolution most similar to the dust clouds orbiting Tabby's star. And you might wonder, why would we ever ask that question? But it actually has a lot of information in terms of where the orbit of this dust cloud might be. So orbit period of revolution most similar to the dust cloud orbiting Tabby's star. We have to go back to the writing 700 period day, 700 day period. So let's go, this is not Earth, nor is it any planet closer to the sun than Earth. So it's not Mercury or Venus. So it's got to be Earth, it's got to be Mars, Jupiter, or Saturn, or Uranus, or Neptune, or Pluto. And if we go to page 14, let's scroll down to page 14. Scroll down to page 14. 14. Not 14. Nope, page 15. Page 15. We have to look for a 700-day period. So 365 and all earlier, not Mercury, Venus, or Earth. But if we look at 687 for Mars versus 11.9 years. 11.9 years is 365 times 11.9, which is over 3,650. So that's not it, it's Mars. Okay. Oops, AI assistant, didn't mean to click on that. So it's Mars. Okay. State the name of the shortwave electromagnetic energy that is mostly blocked out by the dust cloud orbiting Tabby's star. Now, we have to go back to the thing, what they said. Astronomers observed that a portion of the electromagnetic spectrum having wavelengths just shorter than the visible light, just shorter than the visible light. So can we know that? If you are in physics, which you aren't because you're in earth science, most likely you're not in physics, but you might know this already. But there is a diagram that talks about that in the reference table. Just shorter, so just shorter. Increasing wavelength and decreasing wavelength. It said decreasing wavelength just shorter than visible light. Just shorter is right here, ultraviolet. So if you said UL, ultraviolet right there, then you get points there. But how about number 71? Complete the table in your answer booklet by identifying the color and classification of two of the stars in the constellation Cygnus based on temperature and luminosity shown in the table. Color and classification for Deneb have been completed as an example. So if you go to the reference table, this is another one on page 15. This is a really cool diagram because it actually shows stars in terms of their luminosity and surface temperature, and it actually gives us a hint to the future of our own star. What should happen to it? It basically, what happens is the stars tend to follow the diagram, the path of the diagram. So the sun is expected to move to the left over time, but eventually take a right into the giants. Other stars that start up here tend to go to the left and go to the right over here. Okay, so how do we do this? Well, so we have to look at their surface temperature and their luminosity. This graph is based on surface temperature and luminosity. And we have to go for Alberio and Tabby's star. Alberio, I'm going to highlight it in yellow. Has surface temperature of 4,400 degrees and luminosity of 950. 4,400 and 950. 4,400. This is another logarithmic graph. Here's 4,000, here's 5,000. So 4,400 is between 4,000 and 5,000. I'm going to draw a vertical line up. And 950 for the luminosity. 950, so it goes 100 and 1,000. So just below a 900, just below 1,000 is 900. So there we go. So what is the color? And you could have said yellow, anything between yellow and orange. I'm going to go ahead and say yellow-orange. If you had said yellow or orange or yellow-orange, would have been accepted. And then the classification is right smack in the middle of the giant section. So Alberio is a giant. Notice just from the surface temperature and luminosity, you actually know what kind of star it is. That's amazing. And then Tabby's star, I'm going to do that one in blue. So I'm going to highlight it. Might as well highlight it in cyan, which is not technically a blue. Also not technically a green. It's its own color. Tabby's star, we have that it is 6,200 degrees and 1.5 luminosity. 1.5 luminosity. So let's go for that. 6,200 degrees just to the left of 6,000. So I'm going to go right there and draw a line. Right there and draw a line upward. And 1.5 luminosity. 1.5, 1 to 10, so it's really close to 1, just above it though. Really close to where the sun is, isn't it? So it's close to between yellow and white. So if you had said yellow, okay, yellow, white, you'd get your point, your credit for that. You could have also said yellow, since it's closer to the yellow. Um, but now the region it's in is very much this main sequence. So main sequence. Okay, that's cool. So that's full credit for 71. And we have some really cool stars in this list, like Proxima Centauri is the closest star to our own, and Barnard Star, which will soon be the closest star to our own. Barnard Star is actually coming very close to our solar system in a not very distant future. Um, that'll be fun. That'll be a nice, interesting look in the sky. You'll be able, it'll come so close that its movement will be very obvious throughout the sky over 1 year versus the next. Stars, generally speaking, don't move too much in the sky because they're so far away that their sidereal motion is very slight. But we're down to number 72 to 74. This is exciting. We're almost done. This is an 85 question test. I mean, this is a big, big deal. Base your answers to 72 to 74 on the weather map below and on your knowledge of Earth science. The weather map shows the high H and low L pressure centers and fronts across the United States on a January morning. The darker gray shaded areas that look like dirty spots show radar images of precipitation, snow, rain, etc. A partial station model represents weather conditions in southern Texas. Okay, I see that down here. Okay, and two different types of fronts are represented along the lines from X to Y. Where's X? To Y. What X to Y? Two different types of fronts. Oh, I see one type and another type. Okay, from X to Y. Identify the two fronts represented along line X and Y. Now, I actually do happen to know what these fronts represent. I noticed that these are pointing in opposite directions, and these are pointing all in the same direction. But if you don't know, I mean, when I learned it, I literally learned it from Earth Science class. So it's not like surprise I know it. I literally I learned it when I was in Earth Science. And here are the fronts. Oops. Let me do that. Okay. Here are the fronts. So the two fronts represented. So we see this one has a ball on one side and a triangle on the other side. Definitely a stationary front. So stationary. Right here. But then it's followed immediately by triangles all in the same direction. Here's a cold front. So stationary front. And a cold front. Full credit there. Okay. The next one, identify the compass direction towards which the low pressure system located just south of New York will move if it follows a normal storm track. Normal storm track. So they do accept a few different answers, but I do want to point out here that this piece is going a little bit north, but this piece is going east. So if you said the combination of these two, if you would be right. Okay, and you do need to kind of know it's just kind of coincidence that the storms tend to, not always, but tend to kind of follow the track that the coast of the Earth of the United States follows. That's it is absolutely coincidence, but I've always visually noticed that. That's why, like when we have hurricanes, they're almost always just following our coast. But it's absolute coincidence that 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 the United States is shaped that way, and that the storms go that way. It happens to be that the this shape is just matches the tip of the north part of Africa when Africa and North America were connected. So that fact is just coincidence. So storms tend to follow that way. If you had said northeast or east, you would have gotten credit. I chose northeast, although they would have accepted east or northeast, following the cold front and the occluded front. That's located there. Okay. So número 74, complete the table in your answer booklet by filling in the values of the 4 weather variables that are represented by the station model. 4 weather variables. I see 3 numbers. I see 3 numbers here, right? So how do I get those numbers? And what do they mean? I initially don't know. And I'll be honest, this is not one that I have ever memorized for some reason. I do more and more and more of these, and it kind of sticks a little bit more over time. But again, this is not one that I've memorized. I'm gonna have to move that moon in a second. Okay. But if I look at the numbers here, so there's a 46 on the top left. That's the air temperature. So the air temperature is 46 degrees Fahrenheit. They did give it in Fahrenheit. That's important. Then that's this number over here. Now I'm going to choose a different color just so that we're clear here. Then this 37 is down here. That matches the dew point. So the dew point, we have to ignore the number that's written in this model. We have to go to the map. The map is the number that we're looking at, 37. So the dew point is 37. And then there's this number up here, which I'm going to do in black. I'm going to circle in black. This number up here, 217. And 196. And this is one where you just have to know. I don't know why barometric pressure is given as a 3-digit number when it is a 4-digit number. But notice that they actually tell you what this 196 represents. The 196 represents the last 3 digits without a decimal. So the 196 represents 1096 millibars. 1019.6. 1019.6 millibars. So literally, the 196 represents the 19.6, the last 3 digits. It's weird. And if you think it's weird, I agree. So that means that the 217 represents 1021.7 millibars. So weird. Okay. And then there's this 4th digit. What is this 4th number? And if you look over here, I'm running out of color, so I have to choose a pen. I'm going to choose this pen. The amount of cloud cover. And notice that this represents approximately 75% covered. So the black is covering 75% of the circle. So approximately 75% covered. This circle is completely white, which means that this represents a 0% cloud cover. And there's my full credit for that question. All right. Base. I forgot to put space here, but I could put the space now. Let me put a little bit of space here. Let me bring the moon and sun down. Okay, so that we don't mix the work for those. Base your answers to questions 75 and 76 on the map below and on page 51, the data table on page 52, and on your knowledge of Earth science. Map 1 shows the area where the total lunar eclipse was visible on November 8th, 2022. So I look at that real quick. I see that. Okay. And then map 2 shows the area where the total eclipse was visible on April 20th, 2023. So I look at that real quick. and I see a very much smaller area. Okay. The data table shows the data, type, and duration of totality for each total eclipse that has occurred or will occur at a specific location during the years 2022 to 2025. So this is where the table is. And the key is where the area where the total solar eclipse is visible, and this key is the area where the total lunar eclipse is visible. Okay, cool. Determine whether each of the eclipses shown on the maps were visible or not visible to an observer in Hawaii. In your answer booklet, circle visible or not visible in the line next to the data table. Or again, this is Hawaii. So do you have to know where Hawaii is? Well, yeah, but there's Hawaii. Okay. So November 8th, 2022, the lunar eclipse. Let's go there. November 8th, 2022, the lunar eclipse. Was it visible in Hawaii? Hawaii's right in the middle of it. So yeah, visible. And then April 20th, 2023, solar eclipse. Is the solar eclipse crossing Hawaii? Actually, Hawaii is very far from it, so not visible. Número 76, number 76. On the diagram in your answer booklet, place an X on the moon's orbit to indicate the position of the moon on September 7th, 2025. And you're like, how would I know that? That's a year and a quarter from the day you took the regions. Except that the table, I mean, it has to be based on the information in the problem. So, and there it is, September 7th, 2025. We have a lunar eclipse. So that's why I put these pictures here. Here is what a lunar eclipse looks like. Literally, well, this is a partial lunar eclipse at this point, although we're almost at totality. The lunar eclipse literally is caused by the Earth casting a shadow onto the moon. The Earth is always casting a shadow against the sun because the Earth and the sun are close to each other. So what happens to be in the shadow of the sun? Well, sometimes nothing that matters. Occasionally, once or twice a year, and sometimes rarely 3 times a year, the moon crosses the Earth's shadow. And then you get a lunar eclipse. So what is happening at that day? It's a lunar eclipse, which means the Earth is casting a shadow from the sun. So the sun's rays are going to the Earth. The sun's rays are literally kind of going here and casting a shadow right there. A fun fact, it's really kind of more V-shaped, but it's kind of more V-shaped, but that's doesn't matter so much. And then there's another piece of the shadow that's like V-shaped in the other direction. But the point is that the moon has to be here. Oops, I shouldn't put an X there, a dot there, because they said to place an X on the moon's orbit to signify where it is. Anywhere between that, between where the shadow would be cast, is a valid answer. Okay. So that's the answer to number 76. Now 77. Let me just check real quick that to make sure that these are not related. Yes, they are not related. Number 77 to 78. Base your answers 77 to 78 on the diagram below and your knowledge of Earth science. The diagram represents the North Pole view, the North Polar view of Earth as viewed from space on September 23rd. The curved arrows indicate the direction of the Earth's rotation. So the Earth is rotating counterclockwise. State the number of degrees Earth's axis is tilted to a line perpendicular to the plane of its orbit. Now, this is a place where I'm a little bit of an enemy of the way the Regents is graded. I just want to be clear. The answer is 23.5 degrees. But why would I say that I'm an enemy of the way the Regents is graded? It actually is a fact that there's obviously some decimals associated to that angle. And it turns out that the decimals are 23.43 degrees, which technically rounds down to 23.4 degrees. But they didn't include 23.4 degrees as one of the valid answers in the grading. They included only 23.5 degrees. I don't like that. After all, some people know math, and some people know little details of earth science. So they might happen to know that the angle is actually 23.43 degrees, and then that rounds to 23.4. But, and nowhere on the reference table does it mention 23.5 degrees. So, do we need to know at 23.5 degrees? Yes. And let's just confirm. I looked multiple times, and I just want to make sure. Again, I'm not deleting any mistakes that I do. So if I'm actually wrong about that, I'll admit that I'm wrong. But I'm looking for the table that talks about the Earth, and I'm looking for the tilt of the Earth. Let's see, mean distance from the sun, period of revolution, period of rotation, eccentricity of orbit, equatorial diameter, mass, and density. So that angle is not here. Okay. I'll even do a control F, 23.5. Nowhere on this document does 23.5 degrees appear. So I don't like the fact that the regents gave the answers 23.5. What if somebody said 23.4 and the grader didn't know that that's a valid answer? Not an so I'm an enemy of that. Like, I don't like the fact that the regents was not careful enough. So this is me wagging my finger at the regents creators. That said, let's go to number 78, number 78. Explain why a Foucault pendulum located on the Arctic Circle appears to change direction as it swings. So a Foucault pendulum is a really cool apparatus that it swings and it's heavy, okay? So it swings and it's heavy, but it's attached to a platform, let's say. And that platform, so it's attached to a string. And then the Foucault pendulum tends to be very heavy. So usually you use a pretty large mass on the bottom, okay? And then the pendulum swings back and forth. Now, a fun fact, when an object has momentum, it tends to resist motion due to an outside force. Well, there is a rotation of the Earth. The rotation of the Earth is attempting to impart momentum onto the Foucault pendulum, and it does do so just at this common point on top, at that special point on top, which is such a small point relative to the mass of the pendulum and relative to the amount of momentum that the pendulum has, because the fact that it's moving so much and swinging so hard. So what happens is that as the Earth spins, the motion of the pendulum stays the same. Well, what happens? Literally, if you imagine you're on the North Pole, you are standing in the North Pole, you are rotating, you're literally rotating, How much are you rotating? Well, once per day, right? But the pendulum is resisting that motion, so the pendulum is swinging like that, back and forth, left to right, while the Earth is turning. This pendulum is only going left to right. Notice that the pendulum never turned. The Earth is turning, but the pendulum is not. So the pendulum, the Foucault pendulum, actually can confirm that the Earth is rotating. So explain why the Foucault pendulum is located on the Arctic Circle, appears to change direction as it swings. So you could say it a lot of ways. I use the word because the pendulum's inertia resists the Earth's rotation as it swings. It does not rotate as the Earth rotates. But you could also have said something as simple as the pendulum. Oops, switch to a constant color. The pendulum swings in one direction as the Earth rotates. Okay. I will say another fun fact. So I know that there's a small percentage of the United States population that believes that the Earth is flat. It's actually rare for a young person to believe that the Earth is flat. It is a lot more common for a for an older person or a person who's just never been exposed to earth science to believe that the earth is flat. Do understand that this is a fact of science. The earth is round. Again, data. We only go by data. We have pictures of the earth, right? We have satellites. We have astronauts in space. They take pictures. So we know the earth is not flat, it's round. However, suppose you're one of those people that believe that the earth is flat. And there are some unfortunately famous people who do believe the earth is flat, but suppose that you believed it. You can send rockets with cameras to take a picture of the earth and prove it. You can do a lot of things to prove it. It's the thing is that every point of data proves that could prove flat versus round is consistent with a round earth. There is no series of data points that all together prove that the earth is flat. You might say, well, one piece of data doesn't contradict one versus the other. Another data point doesn't contradict one versus the other. But when you combine a lot of data points, they actually can't occur with the same like flat earth model, but they all can occur with the same round earth model. If you can't have a flat earth with one model, well, then the earth isn't flat. But if all the data points towards a round earth, well, then the earth is probably round. And why am I mentioning that? Suppose that some catastrophe happened and all humans had to go below the earth, like they did in Jules Verne's map. Then suppose everyone was literally underground their whole lives, but we were able to communicate with each other, phone lines or internet or something like that. Maybe the satellites didn't get destroyed. I don't know, whatever. So it turns out that you could still prove that the Earth's flat without ever looking out into space with Foucault pendulums, because at nearer to the North Pole, Foucault pendulums spin and completely. Nearer to the at the equator, the Foucault pendulum doesn't rotate at all. At the North Pole, the Foucault pendulum rotates completely, and then mid latitudes, the Foucault pendulum rotates partially, but not all the way. So the rotation of the Foucault pendulum is not just a function of its momentum and Earth's rotation, but it's also a function of latitude. So if you have everyone on Earth, even in dark rooms without any light, just swing a bunch of Foucault pendulums and then communicate with each other. This is how much mine swung. This is how much, or how much mine rotated. This is how much mine rotated. And you make a map. Eventually, you find out that the model that fits the rotation of the Foucault pendulum, literally round Earth. So you literally could prove the Earth is round if you were blind. So the Earth is round. Let's. I'm not knocking flat earthers. I know I'm really not, because it takes a certain amount of exposure to realize that the Earth is round. Scientists had to prove it. Scientists had to do a lot of hard work to prove that. So if you happen to be exposed to the beliefs of people who believe the Earth is flat, then you're literally just gonna go ahead and believe that. And especially if you have a conspiracy theory minded brain, then you might believe it. But there is no conspiracy. I mean, every single data point proves that the Earth fits the round Earth model, including literal pictures of the Earth that we've taken. Okay. Now, base your answers on to questions 79 through 81 on the block diagram below and on your knowledge of Earth science. The diagram represents the magnetic orientation of the sea floor bedrock on both sides of the Southeast Indian Ridge. The area of the igneous bedrock and its distance in kilometers from the ridge center are shown. And I look real quick at the diagram, south, north, Southeast Indian Ridge, and I see a bunch of ridges that look equally, interestingly spaced, but similar on the left and right. C4 bedrock, millions of years, is 4 to 0 back to 4. And then I see a distance 150 to 0 to 150. I see a key normal polarity, which is the current polarity of the Earth's magnetic field, and then reverse polarity, which is darker gray. Number 79, número 79, determine the age and magnetic orientation of the seafloor bedrock located 80 kilometers south of the ridge center. 80 kilometers south of the ridge center. Okay, 50, 60, 70, 80. Now I'm going to draw a line perfectly vertically up as best as I can. The age. age 2 million years. Okay? 2 million years. I think I put the answer. There we go. 2 million years. And then the magnetic orientation, it's right in the middle of the light gray, right? Light gray, normal polarity. All right, numero 80, number 80. Identify the two tectonic plates that are diverging in the southeast Indian Ridge. So if you know this by your brain, again, congratulations. But I am going to go to page 5. Do you need to know the page numbers where all this is found? Actually, no. You just need to be able to leaf through it. And I hope that you've leafed through it enough times during the school year that you know where these are. This is the this is the again the southeast Indian Ridge. So I have to look for the southeast Indian Ridge. Here is India, right here. So I'm gonna use India to look for the southeast Indian Ridge. Here's the mid Indian Ridge. Here's the southeast Indian Ridge. So here's the data that I needed. So which two plates are splitting? The plate right below it, the Antarctic plate, and the plate right above it, the Indian Australian plate. So there's my answers. The Antarctic plate and the Indian Australian plate. That's it. And now 81, explain in terms of cooling rate why the surface oceanic crust forming at this ocean ridge is most likely basalt instead of the gabbro. Basalt instead of gabbro. Okay, so where do I go for that? That's right in the, it's got to be something with the cooling rate, right? So let's go for this table. And where is basalt and gabbro again? So basalt and gabbro are right here. Okay. And I don't need the bottom of it, luckily. So I'm just going to paste this right here. Okay. Basalt instead of gabbro. So I'm going to highlight the basalt. And I'm going to highlight the gabbro. I'm going to highlight the gabbro in a different color, about yellow, gabbro. And I see the environment of formation. I see a scheme for igneous rock identification. I see crystal size and texture. They don't mention crystal size. They don't mention texture. They do mention where it's located. So there's intrusive plutonic, which is the gabbro. And then there's extrusive volcanic, which is basalt. Okay? So how can we determine that based on the information? So the rock, if you look in the plate formation, these are splitting apart. Let's go back to the ridge. I gotta rotate this again. These are at these points, these are splitting apart. You can see the arrows are splitting apart. So what you have is extrusive or volcanic rock. So that makes a lot more sense. Now, here it says it in terms of cooling rate. So what about the cooling rate? There's nowhere here does it talk about time, right? But if you have volcanic rock going into the ocean, that rock cools quickly. So the rock, the reason is that it could be basalt, is that the rock cools quickly on the surface. Okay. Let's rotate this again. Let's see. Yes. One second. I just wanted to take a quick look. I'm not deleting my quick look in this. I just want to see. I wanted to make sure I'm not missing anything for you. Okay, we'll leave it at that. Good. So now actually we are at 82 to 85. These are literally the last questions. If you literally made it this far, I do think that I've earned your subscription, and I do appreciate it if you would subscribe. That's what helps me. And to the 800 and change subscribers, let's see how many. You probably saw it just now how many subscribers I have. It's going to appear in a second. To the 800 and change subscribers that have subscribed already, I do appreciate it. You're the real champs, the real heroes for me. That is what allows me to make these videos. As you know, these videos are and always will remain free. But in order to do that, I do have to, and that's my channel, JuanTutors.com. I do Juan Tutors, 834 subscribers. Did I gain a subscriber since the beginning of the video? I think I might have. I know earlier today I was 828, which is great. So, so but the reason I do this is, and I do it for free, is to give free access to quality education. But based on that, like one of the ways that I get paid is by you subscribing. Because right now YouTube gets to keep the entirety of the money generated by this video. That stops being true when I get to my 1,000 subscribers. So I do appreciate that your subscription if you feel like I've earned it. And if you're at this point, I think I have. Please do. But I'm gonna stop asking for that again. I'm just gonna keep going. The last thing I'm gonna say is I wanna wish you good luck in the regions. I wanna say you've gotten to this point, which means that you're willing to work as hard as possible to get the best grade on the regions. Do the best that you can. Use your logical mind to answer questions, but definitely use your logical mind to eliminate answers, because even if there are things that you don't know in earth science, people are actually just naturally better at eliminating things that don't make sense way more than they are at eliminating things or guessing at what is true. So focus on what doesn't make sense or is incorrect based on the problem's information, and you will maximize your grade that way. Don't be afraid to use your reference table. Keep working hard. And if you have time, I would go back and make sure to redo any questions that you got wrong. If you did choose an answer for every single question, I would then review only the ones that you got wrong uh, in this video. And if you do that, then you will maximize your grade on this regions. But let's go for 82 to 85. Herkimer diamonds. So not diamonds, by the way. Herkimer diamonds are actually quartz crystals that are double terminated, pointed at both ends, and found within exposed outcrops of dolostone around the Mohawk River Valley. As you can tell, I'm really excited. The dolostone was formed about 500 million years ago in a shallow sea that was filled with sediment from the eroded ancient Adirondack Mountains to the north. While buried, cavities were formed in the dolostone by a slightly acidic ocean water. As sediment buried the rock, crystals grew in the cavities, slowly creating quartz crystals of exceptional clarity. The quartz crystals in the cavities are believed to have formed during the Carboniferous period. So Herkimer diamond in dolostone cavity. And this is a picture of it, really pretty. 82. Identify the chemical composition of quartz that makes up a Herkimer diamond. If I slide to page 16, I am here. Okay? Here is the composition, SiO2. Composition, SiO2. So that's the composition. That is SiO2. And I am 3 questions away from a perfect grade on this regions. I'm super duper excited. Identify one physical characteristic of a Herkimer diamond other than its color, that allows it to be used in jewelry. So there's a lot of options, but remember they did say physical characteristic. So if you gave a non-physical characteristic, unfortunately, that's not credit. Like for example, if you just said it's really valuable, great, but that doesn't make it. That's not a physical characteristic. But if you look at the hardness, and they said other than color. So if you said the hardness of 7, that's great. Hardness. After all, you don't want to put a rock on a ring and like you wash your hands and it dissolves, right? So hardness is definitely a valid answer. Oop, I don't know why that's happening. Okay, cool. And other answers you might give are like they said other than the color, right? So the luster, why is this here? Go away. You could have also given a glassy luster, hexagonal crystals. You could have given any of that, but I chose hardness as my answer. How about the 84, 84? Identify the orogeny that it was responsible for the metamorphism of bedrock now exposed in the Adirondack Mountains. And what is orogeny? Orogeny is a process in which Earth's crust is folded or eroded or deformed by lateral compression to form mountains. That's a lot. So orogeny is literally how certain mountains were formed. And these aren't a process. An orogeny is a process. So each orogeny is given a name. Okay. So where do I go for that? Now page 9, I got to rotate it back. Okay. Where is Adirondack? Adirondack. There it is. Oh my God, it took a while. There we go. The Glenville orogeny, the metamorphism of the Adirondack bedrock now exposed. The metamorphism of the bedrock now exposed in the Adirondacks and the Hudson Highlands. There we go. So it's the Glenville orogeny. Okay. That was a mission to find. Okay. So the Glenville the Grenville, sorry, not Glenville, Grenville. Spelled it right in my work, but not just now. Orogeny. Okay. And then number 85, the very last question, one question away from a perfect grade. In your answer booklet, circle the term that describes the relative age of the Herkimer diamonds compared to the relative age of the dolostone. So this is one of those questions again that I told you, thinking about geologic time versus like building a cake type of thing. Again, in your answer booklet, circle the term that describes the relative age of the Herkimer diamond compared to the relative age of the dolostone. Explain how the evidence cited in the reading passage supports your answer. Use the Herkimer diamond and dolostone in your explanation. So the relative age of the Herkimer diamond relative to the age of the dolostone. So the question is the Herkimer diamond older or younger or the same age of the dolostone? And actually, the answer is, if you read the passage again, it's actually younger. Because if you go to the passage, dolostone was formed about 500 years ago in the shallow area that was filled with sediment from eroded ancient Adirondack Mountains to the north. While buried, the cavities were formed in the dolostone by the slightly acidic ocean water. Then, as the sediment buried rock, crystals grew in the cavities, slowly creating the quartz crystals. Which one happened third? So make the layer of the dolostone, take some cavities out, put in some quartz crystals in there. The quartz crystals are younger. So in the reading, the Herkimer diamonds are younger because they formed in cavities cavities of the already formed dolostone. And that's it. Perfect grade on this Regents. Congratulations. Recommend going back to only the questions that you got wrong, going back and rewatching those. And thank you for watching. And I'll see you in the next video.